So good morning, everyone. So let's start the session on topological protected spin textures, fundamental application, the second part of this symposium. And our first speaker would be Sebastian Bustingori, who is here in the room. And he will talk today about response of chiral solid on lattice to spin polarized currents. Please, the floor is yours.
Okay, good morning, everybody. And thanks the organizers for letting me tell you about this story. This is a work, let's see if it works. Should be switching, but it's not. No, that's not me. Yes, but it wasn't working. So, sorry. Okay, here I am. This is a work done in collaborations with people in Zaragoza, where I am right now working. This is a work with Javier Campo, Victor Aliena, Athanasios Athanasopoulos, who was there for a year. And mainly a work by Santiago Osorio, who is in Bariloche, Argentina, in an Institute of Nanoscience and Nanotechnology. So I will start with a brief introductions, fast introductions through skirmions and protected textures. And then I will talk about stability and dynamics of the chiral solid lattice under the action of spin currents. And finally, I will talk a bit about stability and creation and dynamics of the single chiral soliton state. So let's start. As you all know, in this manganese silicon system, we have an A phase in the phase diagram, which consists of a skirmion lattice. The skirmion lattice is stabilized by exchange interaction, which favors ferromagnetic states, and DMI interaction, which favors rotation of the magnetic state the rotation between nearest neighbor magnetic states, which favors 90-degree rotations. And there is a competition between these two effects. And as a result, what you have is an helical state, indeed, where the pitch length of the state, of this helical state, is given by the ratio between the Dialoshinsky strength interaction and the exchange interaction. So with this in mind, now we can interpret the skirmion lattice as the result of three in-plane helical states with wave vectors at 120 degrees, like we have here. And so let's keep this in mind, because I will compare with the other state later. But the other thing is that we actually can have single skirmions, individual skirmions in a track, like for instance here. And this is, has been going around a bit, because we have this idea that we can implement this in racetrack memories, where you have or you don't have the skirmion, and this is a 1 or a 0, and you have a stage that you can use to storage memory. Or either you can use for logical gates and stuff like that. This is an idea around that we all know, and we are trying to push forward whether this can be really accomplished or not. But this is something which comes from an old idea of using the racetrack memory with domain worlds. So actually, when you have a texture, magnetic texture like this, and you can put 1s and 0, the idea of the racetrack memory is going again in the discussion. And what we have here is, okay, to run this racetrack memory, we have to do something that we were discussing yesterday in another talk, which is you have to write, you have to move, and you have to destroy your magnetic texture if you want to run this racetrack memory. And this is something you should remember. You should accomplish in some way. So but we are thinking a different texture, and we are trying to think whether we can use this texture in racetrack memories. And these textures is associated with systems where you have monoaxial elimagnetic structures. And this is the typical example. It's a system composed of chromium, niobium, and sulfur. And here you have only one DMI axis, one chiral axis, and then you have only one helical state surviving. You don't have three, but one. Okay? And there, if we have here with three helical states, you can compose the skimion lattice. In this kind of model, you can compose what we call the chiral soliton lattice, which is the analogous of the skimion lattice. So if you put a magnetic field, you will end up with this kind of texture. I will come back to this in a minute. And if you can have a single skirmions, you can thought of the idea that you can also have single chiral solitons in these systems. This is a topologically protected structure because you have a 2-pi rotation, then you have a topological charge simply here. And we are thinking whether we can push the idea of using this in the racetrack memory. Okay, then in this, what you need is to control or to access the dynamic state that or the dynamic response that you will have against an external electrical current, to move it, or to create it, or to destroy it, because this is what you need to do this kind of memories. So let's talk about the stability of these systems. As I said, we have a chiral axis going, in this case, in the z-axis here. And then you can describe the magnetization with two angles here. One is the polar angle, which measures the departure from this chiral axis, and then the azimuthal angle here in the XY plane. And then you have two main directions for the field. One is parallel to the chiral axis, and the other is perpendicular to it. The simplest model that you can imagine to use here contains the exchange interaction, uniaxial DMI interaction of this form, which favors rotations with a wave vector along the chiral axis. And then you have the external magnetic field, and then you need an EC plane magnetic anisotropy, which is typical in these systems. And I put this here to completely reproduce the phase diagram of the system. Okay? But the important competition is between exchange, DMI, and external field. And in the case of zero external magnetic field, you will have the helical state, as I just told you, with a given pitch given by the competition between DMI and exchange. But if you plug the magnetic field, you have different states. So this is the helical state, and I put it here again because I want you to notice that you can represent the helix here in the block sphere, which contains the three components of the magnetization of sphere, so constant unitary sphere. And then this helical state is nothing else than going in a circle in the XY plane here, perpendicular to the chiral axis, okay, this circle here. But if you plug a field in the direction of the chiral state, you will have a conical deformation of the helix, because you have the magnetization going towards the direction of the field. It means that in the block sphere, you now have to follow this circle outside the equator here, and this is a representation of the conical deformation of the helix, which is hard to see here, but it's this circle outside the equator here. More interestingly, if you put a magnetic field in the direction perpendicular to the chiral axis, this is the case here is that you have regions which are trying to follow the magnetic fields, and then 2-pi rotations between these regions. So here you have something following the magnetic field at 2-pi rotations, and the magnetic field again. So this is how the pure helical state is deformed when you have a field perpendicular to the chiral axis. This is called the chiral soliton lattice in the literature. And in the block sphere, we have again a circle going in the equator here, but here what we represent it with different densities in the line is that you have many magnetic moments following the magnetic field. So this is populated, in a sense, densely populated. And then you have a fast 2pi rotation, which means that this is not very populated here. So at the end, we have these 3 different states, which can be represented in the Bloch spheres like that said. In a phase diagram with the field along the chiral axis here and perpendicular here, this is the kind of situation that we have. We have the helical states here, a conical deformation, and a chiral soliton lattice here. And then if you put the field in a general situation here, you have something in the middle, and then you have this line which tells you that if the field is intense enough, you will recover the ferromagnetic, the force ferromagnetic state. The transition between these lines is not something really simple, and you can find in this reference of Masaki here in-depth discussion of these transitions here. But I will focus on this chiral soliton lattice, which is the kind of situation I like to study. So this was already observed by Lorentz microscopy by Togawa and collaborators 10 years ago. So here we have a zero field helical state transverse. So the chiral axis is here, and this is the helical state following the chiral axis in this direction. This would be in the easy plane direction, and this is the pitch of the helix here. And if you increase the field, what you do is you increase the separation between the 2 consecutive soliton or 2pi rotations here. So the pitch is increased by an increase of the field perpendicular to the chiral axis. And at the end, this is where you cross over to the ferromagnetic state. Okay? Then this is accompanied by an increase of the magnetization in the direction of the magnetic field, which has this typical form, and this has been all measured experimentally. So going to the dynamics, we plug the energy density in the Landau-Lifshitz-Kilmer equation, which give us the dynamics here with the damping, and we add the effect of the current through these spin transfer torque terms here, which are proportional to the polarization of the spin current. And we have the adiabatic and non-adiabatic terms, and this is the beta coefficient measuring the contribution of the non-adiabatic term. So we tackle these problems first with treating it as a boundary value problem. So we say, okay, there is a steady motion of all the pattern if you plug a current. So we use this transformation variable here, saying that all the texture is moving at a constant velocity, and we try to solve the equations, the LLG equations in the form of the angles here, using the angles representation in a period of the chiral soliton lattice between the borders here. And you have parameters of the materials here in kappa and HY, which contains the exchange, TMI, anisotropy, etc., and the field. And you have 2 extra parameters here containing the current and the velocity, and some scales and the damping here. And what else we need? We need the boundary conditions. This is just saying that you need within a period to do a 2pi rotation, and that you allow polar deformation here. The polar angle, if you are exactly in this plane, would be pi/2, but here it's a free parameter, so you allow for conical deformations. And besides, you need continuity of the derivative at the borders, which is expressed in these conditions here. At the end, if you force to solve these equations with these boundary conditions, what we found is that they are only solved, they have solutions only when this parameter omega is equal to 0, which means that the velocity this should be equal to 0, so the velocity is linearly proportional to the current, and you have the mobility here only dependent on beta over alpha and the parameters of the current. If you plug this inside this gamma parameter here, so gamma now is proportional to the current, and this equation has a solution only when this gamma parameter is below a critical value, which means that you have a critical current above which you won't have a steady motion solution for this equation. Okay? Going to the simulations, you can observe this using MUMAC simulations. If you measure the velocity of the chiral soliton lattice with the current, the response is linear. The mobility is exactly what we found with the analytical approach. And here you have different number of solitons because this implies that the mobility is independent of the density of solitons. So it does not depend on the external field neither. And that's why all is over the same straight line here. Furthermore, when you plug in the current, you can measure magnetization along the chiral axis, which coincides with the current here, which means that you should have a deformation of the conical type of deformation. And that this can be observed also if you plug a picture of the steady state solution moving at a constant velocity. You see the 2-pi rotation between nx and ny, which is this big sinusoidal signals, and then a small sinusoidal signal here, which is the magnetization along the chiral axis. Okay, so it means that you have due to the current, magnetization signal along the chiral axis. And this is also observed here. One of these periods here is here. So at 0 current, the polar angle should be pi over 2. But here you have something which is more than pi over 2, which means that you have a conical deformation of the spiral, which is different in the middle of the soliton than in the borders here. And this is the 2-pi rotations at different current 0 and finite current, which is slightly modified. In the Bloch sphere, this is not a perfect conical deformation due to this sinusoidal signal. What you have is a conical deformation. It's slightly misoriented. It's not oriented along the chiral axis, but it's oriented along a different direction. Then this can be described by 2 parameters. One is the orientation angle of the cone, and another parameter which is the aperture of the cone. So this cone is not as a conical deformation due to the field, but it's slightly deformed. Okay. And you can follow how this is depending on the current, because you reach stable values for the orientation and the aperture of the cone. And then if you plot these values against the current, you have that the orientation angle increases and the aperture is decreasing. So it means that you are going up, but slightly decreasing the angle of aperture. Up the critical current here, and here you can see that at the critical current, it doesn't mean that the cone is fully closed. Okay, that's important. But what's happening beyond the critical current? What's happening there is that this slight conical deformation is misoriented or not oriented along this axis. The angle is increasing. This is shown here. This is orientation angle which is increasing. And at the end, this is no longer a cone here, but it ends up with a point, which means that you reach the ferromagnetic state in the direction of the field. So you plug a large current in plane, and you end up with the ferromagnetic state along the field, which is perpendicular to it. And this means that the orientation is going to pi over 2, and the aperture is going to 0, essentially. At the end, you will have a phase diagram like this one. So at 0, this is current, this is field. At 0 current, you have the chiral soliton lattice, and then if the field is large enough, you end up at a ferromagnetic state here. But if you, at finite field, you increase the current, you will have a chiral soliton lattice moving at constant velocity first, linearly with the current. And then you have an instability here, which is this kind of instability here, which forces the ferromagnetic state along the direction of the field. But if you increase the current even more, you will destabilize this ferromagnetic state because you induce a lot of spin wave of low energy in the system, and then the force per magnet is no longer stable, and this is discussed in this paper. For instance, it's something that people have been found in different situations when you have the ferromagnet and the current. But I just pointed this region here because here you have a crossing between the two lines. This one, which is the instability between the chiral soliton and the force ferromagnet, and this one, which is the instability of the ferromagnet. And there's something strange here, which is that you can pass directly from the chiral soliton lattice to this region of unstable ferromagnetism, something like that. So it deserves some more thoughts here. But what is interesting also is that these two states, they have very different magnetoresistive values. So you can have a low magnetoresistive state or a high magnetoresistive state. This has been measured many years ago. And it means that if you follow this line, for instance, and you trigger square pulses of the current, you may start with a chiral soliton lattice, for instance, here, and then a pulse up to this current and 0. This will maintain metastable state the ferromagnet, and then you are switching between high and low magnetoresistive states. But if you plug a square pulse with a current large enough to destabilize these ferromagnetic systems, and you turn it off, you will relax to the chiral soliton lattice again. So you can switch between high-low and low-high magnetic state. This is interesting, for instance, not only to have this signal of two different magnetoresistive states, but to try to find these lines using just magnetoresistive experiments, and you don't have to observe the lattice with Lorentz microscopy, for instance. This is much, this is a different route to find this kind of phase of diagram. Okay. Now, rapidly, I'm going to the single chiral soliton, which is this idea that you can actually have individual solitons, like you have individual skyrmions. And this can be thought of as a 360 domain wall, if you want, between a region with up magnetization, 2-pi rotation, and a region with up magnetization again. It has many similarity with the pi domain wall, the 180 domain wall, but here you cannot move it with a magnetic field, which is what you have usually with domain walls, because magnetic fields favors both domains in a general sense at both sides of this soliton here. So you have to use the current. And we can show that this structure is metastable in a huge region of the diagram. Here is magnetic parameters in this kappa variable. So this line corresponds to this chromium, niobium, sulfur material. This line would be the limit of the stability of the chiral soliton lattice against the field. And what we see is that in all this region, this single soliton state is metastable, and outside this region, it's not even stable in a general sense. So we can find these structures here. Actually, if you measure the energy as a function of the magnetic fields of system with different number of solitons, you can see that here is the chiral solitons with different, the stable state is the chiral soliton lattice with different number of solitons. Then this is unstable, and the ferromagnetic state is the stable state here. But the first metastable state here in this region is the single chiral soliton state. Okay, so there's a huge region of metastability, and since this has the protection of the 2-pi rotation in a topological sense, it's metastable with a very long lifetime. How can we get this state? What we propose is that you can plug currents in different directions on the system. So you make the solitons move in opposite directions to the middle of the system. This destroys the solitons one by one, in steps one by one. And at the end, you can end up with a single soliton when you turn off the current. Okay? And once you have this, soliton is metastable with a almost stable in a sense that it has a very long lifetime, and then you can manipulate it. Indeed, if you apply to the system of opposite currents, square pulses of the current, there is a huge region in this phase diagram of the current versus magnetic field when you can't end up with one single chiral soliton. So it's not something that you have to fine-tune. There is a huge region where you can find it. And then once we have the soliton, we plug the current and we see how it responds. Since the mobility does not depend on the number of solitons, we have exactly the same mobility here. And the deformation of the moving soliton is described in this figure, where you have, particularly this figure here, is how the polar angle departs from the pi over 2, which means that at one end you need to have a pi over 2 because you have the ferromagnetic solution. At the other end, you need to have the pi over 2. So in the middle, you have a conical deformation, which is this peak here. And in the Bloch sphere, is kind of deformed cone. It's no longer a cone because here is the ferromagnetic state, and then the 2 pi rotation going with a polar angle here. And as I said, the mobility is the same as before. And you can measure, for instance, how the width of the soliton is reduced by the current. And again, we have a critical current for the stability of this object. Beyond that, the object is destroyed. So what we have at the end is that we have a proposal to write this single chiral soliton state. We can move it with the current, and you can destroy it with the same current if you can manage the values. So in conclusion, we have studied how the chiral soliton lattice responds to external currents based on stability analysis 2. And we have this phase diagram with a different state that you can prove via magnetoresistive measurements. And we can show that you can get metastable single chiral soliton states in a wide range of this phase diagram, and you can move it and control it. As in the talk yesterday, it's important to write it, move it, and delete it, in a sense to put it back in the racetrack. There is a long way between this kind of approach that we have and the racetrack, of course. And this should be thought a bit more. There are many things to solve if we want to continue thinking about how to put this in the racetrack. But there are many interesting things also about how this, particularly for the chiral soliton lattice, how all this depends on the thickness, the DMI interaction, the anisotropy energy, and the dipolar term, most importantly. There are some results from last year in this paper, where they work with a similar material, and they found many experimental results which depends on the dipolar interaction, and particularly on the thickness of the sample. And I think we should understand a bit better how this change all the things I've shown here. In particular, the texture will be all deformed. It's not a simple chiral soliton lattice, and we have to understand that. And we also are thinking how disorder and pinning effects might change the response of this kind of system. This is, we think, also important. So with all this, thank you very much for your attention. I think it's enough.
Thank you, Sebastian, for the nice talk. The session is open for questions. We have maybe time for 2 questions, either in the room or online.
I have a small question to your phase diagram of the previous slide, where you show this dependence on different states. Chiral spin lattice, forced ferromagnet, and then ferromagnetic instability. And you argue so that this ferromagnetic instability induced by overcritical current is due to the spin waves, right? Spin wave excitations. But also the forced ferromagnet could have spin wave excitations. They are gapped, of course, due to the Zeeman energy, exchange interaction, and Dzolshinsky-Marie interaction. What is the difference in the spectrum of spin excitation of the forced ferromagnet and in those in the ferromagnetically unstable state? Is the gap closes or the spectral weight changes somehow?
In the simple approximation, if you don't consider the gap, you will end up always with a ferromagnet which is unstable. So in order to cross this line experimentally, you have to cross the gap due to the current, in a sense. I think the difference in the spin waves here is that this tends to have a short lifetime, and it ends up in a ferromagnet again. And these are low energy, very lifetime, let's say, spin excitations that put you away of the ferromagnet in a sense. As much as I understood, this was never experimentally observed, but maybe I'm wrong. But this is a theoretical proposal that is many articles I read before, and it seems to be something very clear, but I don't, maybe just that the currents are very large. I mean, the density currents is the problem in all the speech here. The value of the density currents is always the problem, because in order to reach this 10 to the power 12 ampere per meter square, you have to be very careful. And there are many details in this.
So probably you have to melt the sample.
Yeah, maybe. Maybe there is a line here which is melting, but I'm not putting that here.
Okay, so thank you very much.
And there is any other question? Maybe online? Yeah.
Hi, thank you.
Yeah.
I didn't catch how experimentally you would end up with a single soliton. I mean, how?
Yeah, okay, this is a numerical proposal, you know. So you need three contacts here, so you can have two currents in opposite directions. This moves the solitons against each other. So you have this, if you measure the energy as a function of time, you have this increase here of the energy, which means that the solitons are too close to each other, and at the end, since you are continuing injecting energy in the current, they prefer to destroy one of the solitons, and then you are removing one by one the solitons, and you end up here. You have to be careful, because if you don't have these portions here, which are strong ferromagnets, you will have solitons entering over the borders. So this is a strong ferromagnets at the end that force a boundary condition which is appropriate for this idea. I think this is just to show that it's possible in a sense, but we have to work a lot to go from this to something more practical experimentally. Yeah.
Yeah, maybe 10. Plus one.
Yeah.
Very short question. I think there's
Yeah,
one
maybe
over
then.
there.
Thank you for the nice talk. Also, in this case, you have this peak in the energy as a function of time. Also, this kind of thing can produce melting or heating the system or not? What do you think? And the second question is possible to include this kind of process somehow in this phenomenological model, or you need to go more deeply, let's say, first principle calculation? Or
So first, these peaks, I think they relax in the system in the spin relaxation, spin waves. That it's not enough to melt, I think. And to the other question, with this simple model, which is very exchange DMI anisotropy field, I think we can manage to do what we are planning to do, but you have to think of new ways of doing that, new geometries, new. We only play with the current here, but you have to do something else. Maybe put a cross with an Oyster field or something like that to help, or some tip of AFM or something like this, or to help. You need to think a bit more, but the essential ingredients are in this simple model, I think. Yes.
That's it.
Yeah, very short question. So you discussed about this low and high magnetoresistance states, and you proposed the solution to switch between the two states. Does this mean that this system will behave hysteretically? Because if you go in, like, if you send the current, then you go to the low resistance state, but
Right.
then what's the meaning of this phase diagram in that case?
The idea is that you can plug in, you can use this square pulses. And there is a scale here with this, the duration of the pulse. The idea is that you have an initial state, and if you have this pulse, you end up with a metastable state here, which is in some part of this phase diagram.
But
So
this phase diagram, it only applies during the pulse or also after
no,
the
no, no,
pulse?
it's a very short pulse. So the idea is that is long enough to put you here, but once you turn off the current, you have to go to this line or with a stable or metastable state. So it's a way to go all over this phase diagram too. Okay? Thank you.
Hey guys, we should move to the next speaker.
Okay,
So
thank
thank you, Sebastian. So
Thank
I have
you.
here a certificate for you.
Okay, thank you. Thank you very much. So maybe.
Our next speaker is it's a contributor talk from Sabri Koraltan, and while the presentation is getting ready and setting the microphone, so he will talk today about generation of skirmions and antiskirmions by topologically coupled heterostructures.
Okay, perfect. So it's laser, this one, great. So thank you for the kind introduction. And as already said, I will talk about a way to stabilize skirmions and endoskirmion lattices by using 2D metamaterials. And can you click on the presentation? Down one, hold still. Possiamo hablar? Ah, okay. So, ileri değil mi? Tamam, teşekkür ederim. So, thank you. So this is a collaboration between the University of Vienna and University of Augsburg. And it's a long-time cooperation. So the first part was also presented by Timo. And now we wanted to investigate a bit further. But before going into the main motivation, I just want to give a short recap on the topologically protected spin textures. And we will mostly concentrate on the Bloch skirmion, which is a local whirl in the magnetization. So if you have an outer region where we have a ferromagnetic state, where the magnetic spins are pointing down, then at the center we can have a whirl in the magnetization such that we obtain a quasi-particle-like structure, spin texture, which has this topological protection. If we take now, if we would sample the magnetization along this line, then we would obtain Bloch walls, thus the name of Bloch skirmion. For many, the real skirmion, the Nea skirmion, which comes in a chiral system, which is usually stabilized in the using interfacial DMI. In this case, if you sample the magnetization along this line, then we would have nail walls. So that's why. Because this let's say the Bloch skirmions, they're not in a pure chiral system, but depends. So they're usually stabilized in bulk TMI systems with P20, for example. And if they're dipolar stabilized, they rather refer to magnetic bubbles of type 1. And we also have type 2 bubbles, which have only half of charge, and they basically have this surrounding, so it goes basically down and up and then down again, but we do not have this full rotation of the, let's say, perimeter. And in addition to this, we also have the anti-skirmion that we will also investigate in this talk. And now the basic idea is that the anti-skirmion is a topological counterpart to the skirmion. And if we say that this has a topological charge of +1, this one will have -1. And we will basically, let's say, we will see here an iteration of a Bloch, also of Bloch and Nail walls, such that at the end we form an anti-skirmion. And the one thing that we will also use is the magnetic vortex. It's maybe in one of the most known structures that have been investigated intensively. And when it comes to the motivation of our work, is that, as we have also seen yesterday in the very nice talk by Timo, was that we were using iron gadolinium multilayers where we have inserted additional iridium layers, and we were able to observe using Lorentz stem and then later in simulations counterclockwise Bloch skyrmions, clockwise Bloch skyrmions, as well as first and second order anti-skyrmions in the same system. In our micromagnetic simulations, we have seen that we can start with a domain morphology where we have strap domains with tripods or like chiral or not chiral, let's say, domains or strap domains, and upon application of an external field out of plane, then we can shrink down these magnetic domains, and the domains, so the stripes without the chirality, they will break down into trivial bubbles, into type 2 bubbles, whereas those with a chirality would then break down into Bloch skyrmions. And if we have tripods, we could also obtain anti-skyrmions. And we have also seen yesterday that we have a well-known recipe to obtain anti-skyrmions, so dipolar stabilized anti-skyrmions. And here also a closer look on how these two structures could look like. And it's not very visible here, but the stability also differs. So usually the anti-skyrmion is a bit less stable. But in this system that comes basically with a problem, namely we also talked about, so we just had a very nice presentation talking about racetracks, and there was the idea that you should be able to write it, move it, and control it. And this is something you just cannot do here. You have skyrmions, anti-skyrmions, bubbles everywhere. It's very difficult to put them on a lattice, because if you say that so there is this method that you can apply an in-plane magnetic field. You can force your helices or you can force your stripe domains to be along one direction before applying the out-of-plane field. But then you lose the chirality, and then you will only have bubbles, but no Bloch skyrmions and so on. So it's a bit more tricky. And the more important one maybe would be also that we cannot control the chirality of the skyrmions. You have no power to say, okay, I want to have a clockwise or I want to have a counterclockwise skyrmion. And you cannot choose one of the skyrmions and delete them, right? So you cannot just access a system and just delete them. And that's what we are trying to solve. We want to have a system where we can control this. And for this, we are using magnetic metamaterials. And the basic idea of using a metamaterial is that you combine two systems. One of them you know how to control, and the other one you don't. So, and in our system, we will be using our iron gadolinium as the purple layer and as a skyrmionic layer, and then we are patterning a nanodot lattice. And the nanodots are out of permalloy, and we want to, because we know how to play around with permalloy, we know how to control permalloy, nanodots and the rays, they've been intensively investigated. We hope to be able to control the structures underneath. And of course, we are then not limited to nanodots, we can also have nanosquares. But I will not talk about this, but I would rather talk about the anti-square lattice, if you wish, but which is basically very similar to an artificial spinized lattice, which then it's an interconnected artificial spinized lattice. It's just a square lattice. And for the first part, so this is a pure micromagnetic simulation work, let's say, and we have patterned, let's say we have designed our two materials, and in each, so it's a finite difference simulation. In each cell, we start with a random magnetization state, and we first relax the structure, so which means that we are solving the Landau-Lifshitz-Gilbert equation numerically, and we include energy terms from demagnetization, from uniaxial anisotropy, so from PMA, and exchange. So we don't have any DMI in the system. If you relax the structures, then we can see that in the permalloy lattices, we are observing, of course, vortices. So we have chosen the critical dimensions for the permalloy nanodots to be able to host stable magnetic vortices. And you can see that we have blue and red dots. It will be a bit more clear in the next slides. But you can see here, if we don't apply any out-of-plane magnetic field, then we have the polarization of the magnetic vortex core can be either up or down. And we can see that underneath in the skyrmionic layer, we have a structure which starts to look a bit more like a lattice. So then we apply an out-of-plane magnetic field. We go up to 100 millitesla. And at the end, what we're observing is that we can relax a skyrmion, let's say, lattice. But because we started from a random state and we did not really manipulate the permalloy layer on top, what we see is that whenever we have the polarization of the magnetic vortex core, which is not aligned with the magnetic field, we have a skyrmion underneath. And whenever the polarization is parallel to the applied magnetic field, then we do not have a skyrmion. And here we can also see that so even though we apply 100 millitesla out of plane field, we are still having very nice magnetic vortices. So we see that we have a little bit of an out of plane component, but the decisive part, which is the magnetic vortex core, it's still in the system. If you now have a closer look, then we can say that we have here the magnetic vortex, which has the polarization parallel to the applied magnetic field. Then we do not see a skyrmion, and then in the next one where it's anti-parallel, then we see the skyrmion as plotted here by the magnetic induction map. And if you would then sample the magnetization along this line, then we can see here very nicely that whenever the vortex layer, so where the magnetic vortex core points down, so then we obtain a skyrmion, and whenever it points up, then we do not have a skyrmion. So this is as you see that we start with a random configuration. We just like relax the structures. So now we also want to obtain this beautiful lattice where we have a skyrmion at exactly, basically everywhere we have an unload lattice. And experimentally one can achieve this, let's say by hitting, so permalloy and the iron gadolinium multilayers, they will have different Curie temperatures. So if you heat it up only to, let's say, 300 or 400, okay, to 400 degrees maybe, or 400 Kelvin, let's say, or 400, 500 Kelvin, then the permalloy will still be ferromagnetic, but iron gadolinium will already become paramagnetic. So then you can manipulate at high temperatures, you could manipulate the permalloy disks, may arrange them in all in a clockwise manner by applying an X field whatsoever, and then apply a positive field, and then also decide over their polarization. And then cool back down, and then obtain a full lattice of skyrmions. And because we can also pattern the nanodots in desired, let's say, lattices, so we can have a square lattice, we can have a hexagonal lattice, and so on, we can also choose how to exactly pattern this. In this way, we just wanted to show that we can have a full lattice. So we put all to have the same chirality and also the same polarity. And if you have a look at the cross-section, we can see that whenever we have a skyrmion in the skyrmionic layer, the magnetic vortex core rather diffuses into the skyrmionic layer. And maybe at this, I forgot to say, but we do not have any interfacial coupling, so we do not have any spacer layer in between. This is not like the artificial skyrmion lattices that have been already done previously, where you basically have you have some nanodots, and then you have a spacer layer which couples them ferromagnetically to the 1 or 2 nanometer skyrmionic layer underneath. But the dimensions are rather 30 nanometer, so this is wrong, but 30 nanometer of permalloy disk, and then 50 nanometer of a skyrmionic layer. And we can see here that it's fully diffused into the system. In the case where we do not have a skyrmion, then the magnetic vortex core, which points up, is just like more, let's say, a bit more constant, and only when the skyrmionic layer starts, it starts to diffuse a little bit. Okay, and now one more time, we can see that if you plot now the magnetization sample along the x direction, we can see that whenever we have a vortex core, which is anti-parallel to the field, then we obtain the skyrmions underneath, and with the same chirality. As you can see here, they all have the same chirality underneath. But as I said, so I also worked a lot on artificial spin ices, so I wanted to maybe see how such a structure might behave. And in principle, it's also possible to relax vortices in these structures. And note that we have, again, about 30 nanometer thickness. And I was also a bit inspired by the work of Sebastian Gliga, where they had, where they showed micromagnetically that they can also switch by a pulse field, by a field pulse. They can switch the magnetic the core of a magnetic anti-vortex. And what they have done is that they basically apply a short pulse of about 100, 200 picoseconds, and they were able to reverse the magnetic vortex core. So I thought maybe this is something that we can somehow take, so we can also try later to use it to our favor, which I will discuss in a moment. But the basic idea is that to now create basically the ground state of the artificial spin ice lattice, which would be the ice rule. So we have magnetizations in the vortex, let's say, in the host material, in the metamaterial, where two magnetizations points in and the other two point out. So we have the two in, two out rule. It's the so-called ice rule. And this is the ground state of this lattice, because the magnetization will then build closed loops. So we have to go here to the right and here go back up to have everywhere these type 1 vertices. And in this case, we built the closed loops, and that's why we have the long range or the ground state. But in spin ice and artificial spin ice field, people do not use interconnected lattices, but rather stadium shaped like islands and whatsoever. But here we have the interconnected system. So whenever we have this structure, the magnetic configuration is then forced to build an anti-vortex. And the goal was to obtain the anti-skyrmion underneath, which we can see here at, again, exactly wherever we have the anti-vortex core. So we're making use of the exchange interaction to couple the, let's say, to imprint a little bit, or like help to nucleate the anti-skyrmions. Again, we can choose here let's say, the direction by the sense of rotation. So as you can see here, they are 90 degrees rotated, the anti-skyrmions, which might be actually helpful, but I will maybe give that information later. And we can now have, again, a closer look. We can see here that we have the anti-vortex, and this one is the anti-skyrmion. And if we sample the magnetization along this line, wherever we have the anti-vortex core, we can also have an anti-skyrmion in our skyrmionic layer. But there is one point that it's missing, and namely, okay, but not yet, so I forgot about this slide. So we can again have the skyrmion lattice as we wish. We can control the direction, we can control their existence, and this diffuses a bit more. It's a bit more straight, but it comes because the lattice is basically a bit more constrained geometrically. And this is maybe the more interesting part, because as it was also said, so you also have to write them, but also delete them, right? And you want to be able to delete them by command. You want to delete them energetically, you want to consume less energy as possible. And for that, we have, again, our nanodot, and we apply the out-of-plane field to stabilize the skyrmion. Then now we apply a pulse of magnetic field, which is about 200 picoseconds. And it's also only, I guess, 50 millitesla. And what happens upon application of this pulse is that we create the well-known vortex and divortex pair in the nanodot, which then destabilizes a bit the anti-skyrmion. But ultimately, this vortex and divortex pair will then collapse and then reverse the magnetic vortex core, which will then delete the skyrmion underneath. So if you remember, the skyrmion was only stable, or let's say it's stable as long this vortex points opposite to the magnetic field. So when you reverse the polarization of the magnetic vortex core, you automatically delete the skyrmion. And this is allowed topologically because the total topology of the system does not change signs. So you have the skyrmion, which has the +1, and then you have the vortex, which is 0.5, and then in total you do not change signs. That's why it goes over. So you don't need any Bloch point formations to annihilate the skyrmion. And we want to do the same for the anti-skyrmion, and we apply again the pulse of magnetic field. We have the magnetic anti-vortex core. Then we apply the field. We switch the anti-vortex core, and again, without switching the sign of the total topology, we can delete the anti-skyrmion. To briefly summarize everything, we have seen that we can use metamaterials to pattern, let's say, to obtain arbitrary lattices of skyrmions and anti-skyrmions, which would be also first, at least in the simulations, and I hope to see them also soon realized. And the idea is that we can also use this to, so we can delete them or write them using pulses of magnetic fields, but you can also use spin transfer torques. So you can apply an AC current, and it will do the same job because you can reverse the magnetic core also using a spin transfer torque, even spin orbit torque and so on. And the maybe for me the most interesting part would be that we can also move them, so they are not pinned under the nanodots. If you apply a current, you can just move them, and a new skyrmion will be generated underneath, because the vortex core generated the skyrmion, not the exchange interaction. And then if you move the skyrmion underneath, a new skyrmion will be then imprinted, because that's the ground state. And the very nice part would be then now, so we are working right now to realize this also experimentally with the movement, so I hope to be published also soon. But the idea is that in the case of the anti-skyrmions, you can rotate them a bit, right? And then you can apply the current in the 45 degrees, and you can get rid of the Hall angle. So because if you apply the current, so along this direction, you will have the Hall angle. But then if you put your cross 45 degrees and you apply the current to that 45 degrees, then you don't have a skyrmion Hall angle. So you can propel the anti-skyrmions straight forward. So thank you very much for your attention. I hope that's it.
Yeah, thank you for the nice talk. So, yeah, Matthias.
Yeah, thanks. Oh, wow. A very nice talk. Just one comment on slide 15, where you say that the topology doesn't, well, the topological winding number doesn't change sign. If you go to 0, you already have to nucleate a Bloch point. If you go from 1 to 0. So it's not just sign change. I think the important thing is that it stays at finite value with the same sign. Because going to 1 to 0, you need to nucleate a Bloch point.
But this is the point. So this does not. So you really don't get a Bloch point, because the total one. We looked into detail in this,
Okay.
because as you know, detail he was very easy. These are possible.
Yeah.
So we looked into detail into this, and then it really does not build a Bloch point. But it might also be that we have a too large of discretization. That's why we don't see it.
Okay, and then in slide 5, just something that I saw that I didn't see in the talk yesterday. It looks like some of the objects that you have seen here, they seem to be linked. So if you look at some of the objects, there seem to be some contrast even in between exactly.
Yes.
So this means that they are also not free to move independently.
They are, but this is basically, so it's the snapshot is taken at 80 millitesla, and then so there was a stripe domain here, and this stripe domain most probably collapsed at 79.5 millitesla. So now it's just, I took the snapshot exactly when I saw that they are enough structures. So if you increase the field like 0.1 millitesla, then you also get rid of this, so they're really isolated.
Okay, all right, thanks.
Any other question maybe online or no? So for the stabilization that you use, I mean that you employ this permalloy to stabilize the skyrmions, how would they be stable after you try to move them out of the dot? So how? So
this is the main idea of using a skyrmionic layer underneath, because as you can see here, the skyrmions are also stable without having any vortices. So if you have, so you use the vortex to nucleate it at a certain location, but when you move it out, you basically are in this system. So where you do not have any vortex on top, right? But in this system, it's also stable. So if you have in these artificial skyrmion lattices, they use this 1 nanometer PMA stuff, which cannot host the skyrmions outside of the vortex. So it's just an imprint of the exchange interaction, basically. But what in our system, you go out and you're in the skyrmionic system where you can just have the skyrmions and the skyrmions all the time.
Okay, so there would be some energy barrier to annihilate the skyrmion itself. Okay.
Exactly. Yeah. So we also calculate energy barriers, also very high. But again, this is the problem. You calculate energy barriers using micromagnetic simulations the way we do. It's inaccurate because you usually have to go over Bloch points, and then you cannot describe them micromagnetically because you have anti-parallel alignments.
Okay. So if we don't have any other questions, so let's thank again the speaker. Yeah, have here a certificate for you. So yeah, our next speaker and the last of this session is Lufti Arda, who will talk about the investigation on effect of defects of the structural, optical, and gas sensing properties of radium doped zinc oxide nanorods. Yeah, please.
Okay, welcome to my presentation. My talk will be about the investigation of effects on the structural, optical, and gas sensing properties of erbium doped zinc oxide and zinc oxide nanorods. This is the collaboration between three universities. These universities are Gazi University, is the Kastamonu University, and Bahçeşehir University. This is out of the scope. It's a different area, okay? The first. Oh my God, it's not working. Yeah. What is the motivation and for this work? Zinc oxide materials and zinc oxide based nanomaterials such as nanoparticles, nanorods, nanothin films can be used in many fields because zinc oxide is a multi-purpose materials and it is used in gas sensors, conducting windows, varistors, transparent electronics, spintronics, optoelectronic devices. However, the defects that occur during growth in these nano-sized material are still an incomplete issue. That's why it is not used effectively. What is the aim of this present work? We divided this present work in the two parts. First, we investigated zinc oxide nanorods, temperature and the growth time to find the better crystalline materials. After that, we investigate the role of the defect on the structural, optical, and the gas sensing properties of the zinc oxide nanorods. This is the schematic diagram of the production process of zinc oxide nanorods. We can produce zinc oxide nanorods. It's just nanorods, and the second one on the seed layer on the thin films nanorod, like the brush. How we can do this? Okay, if you want to produce just nanorods, we can use hydrothermal routes and directly after the heat treatment is 90 degrees with the different heat treatments and the growth time, we can produce nanorods. The second one is on the nanorods. It's on the thin films nanorods. It's okay like this. First, we have to clean. It's a substrate. It's a glass or the silicium substrates. We use glass substrates. And after that, it's a dipping on the solution and the coating zinc oxide. It's a seed layer. Then use zinc oxide. It's a precursor material. And after that, is use a heat treatment and produce on the seed layer zinc oxide nanorods. When we produce zinc oxide nanorods, the first key question is resultant material is the single phase or not. This is very important. If it is not single phase, then that means you cannot understand that the properties comes from the single phase or the second phase. That's why we use XRD to check it is a single phase, but it is not enough. We need to check with the Rietveld refinement method also. Look at these results are from the XRD. There is on only single as a peak. This is the C direction peak, and this is the single phase. Also, we check with the retail refined method this, and of course, critical growth parameters and the grain size of zinc oxide nanorods obtained from the diffraction pattern. This is the table, and we calculated the C lattice parameter, grain size, strays, and other properties here. We calculated diameter length of the nanorods, aspect ratio of zinc oxide nanorods at different growth times and the temperature. This is the result of the scanning electron microscope from the top surface with for the different temperature and the growth time. I didn't put here, and there is the cross section, but I will move a little bit down. I'm sorry, because this is the, oh my God, where is this? Yeah, look at here. This is the cross section. I forgot to put the above this. Look at the cross section. There is the nanorods on the seed layers. Again, I'm sorry. Okay, I will back very fast. That means I came here. You can see it's a hexagonal nanorods here. After that, we check that is it zinc oxide nanorods or not. This is the EDX mapping images. Okay. And after that, this is the characterization of the nanorods. And after this point, we continue with the optical properties. And we take transmittance of the nanorods, and we calculate using tau plot is a band gap. Result I will show you with the table. Okay, that means transmittance decreases with increasing growth time, also decreasing with the increasing temperature, entering temperature, and the band gap is the opposite. No, it's the same. That means when increasing the growth time, it's also band gap decreases. When we increase it, is temperature, also band gap decreases. After that, it is very important to check defects on the material. Maybe it's right now it's to check is a defect acting on the application. It's very important, and this is the PL measurement results. There is two emission. The first one is the near bound emission, and the second one is the deep level emission. Deep level emission is the visible regions that from the first emission we can check that the crystallinity of the nanorods. From the second emission we can check defects time, but when we take this we cannot understand that sub peaks there. That's why we use fatigue program to check the Gaussian decomposition. Look at after it's this procedure we found it's 9 sub peaks, and the first and the second peaks are for the near bound emission, and I did a mistake, I think. Okay. Okay. Can I move it? okay? There are 9 peaks, okay? 2 of them are for the near band emission, and the other peaks are for the defect types. And as a result, this is for the growth temperature. As a result, with an increase in the growth time, the double charged oxygen vacancies, it is a donor, decreases, whereas oxygen interstitial acceptor increases, however, growth temperature decreases, as a double charged oxygen and interstitial oxygen increases, okay? As a result, we can say that zinc oxide nanorods can be grown according to the defects, donor or acceptor, by selecting the appropriate growth time and temperature depending on the place of use. That means we found that it's using different temperature and growth time, we can change that the defects. This is the conclusion, but the important point I say to you, that's why I will pass this slide. Then, another important point is I showed that the zinc oxide nanorod is we change its annealing temperature and the growth time. Then we doped zinc oxide nanorod with the rare earth element. Of course, we use its metals, transmission metals, and we published many articles using this. That means our goal is when we doped with the rare earth elements to sense some gases and correlate with the defects. I will show some results, but this study is right now ongoing. That's why we have not correlation between defect and the gas sensing properties. Just I will show you some results, okay? That means we doped the erbium with the nanorods. Again, we found it's from the XRD results, phase of the erbium doped zinc oxide nanorods. It is very important when we dope the nanorod with the second element, it is very hard. That means to find changing the second element with the zinc oxide nanorods, zinc oxide is a place. This is the top surface scanning electron microscope, and the other one is a cross section. This is the EGS, and from the EGS we can see is an erbium element here. That means we doped successfully. This is the average radius of the nanorods, increasing erbium doped zinc oxide. After that, again, we take transmittance, okay, and also we calculated its band gap from this site. I think I put two of them. That we can see that when we increase the doping ratio, transmitted decreases. Also, band gap. This is the green one, and the purple. That means band gap decreases too. Again, to understand the defect for fabrication erbium doping nanorods, it's again we took PL measurements, and again we use the with the FITIC program Gaussian decomposition, and we found the defects. Last part is we use carbon dioxide sensing. This is sensitivity versus temperature. This is the sensitivity with the different flowing. It's a carbon dioxide gas, and the time. And again, this is another one. And this is the comparison of sensitivity response time and the response time at the 100 ppm gas concentration. Right now, I told you that we are ongoing this project That means there isn't right now correlation with the gas sensing properties with the defects. Okay, thank you so much. Many thanks to the Bahçeşehir University, Gazi University, and the Kastamonu University in Turkey.
Yeah, thank you, Lotfi. We have now time for questions.
Because
Yes, please.
yeah.
I missed when you
So
prepare
wait a second for the microphone so
Sorry.
people
I'm
online
sorry.
can follow. Yeah,
Yes.
thank you.
When you prepare your samples for X-ray diffraction, do you remove the rods from the substrate or it's all together?
We prepare two different nanorods. It's just nanorods, and the other one is on the seed layers. That means we first took XRD with the nanorods, just nanorods, and then we try to use with the substrate and the seed layer and the nanorods. Because the seed layer is a zinc oxide, that's why I prefer first one.
Yes, also because you're using a Rietveld method.
Yeah, just we have two different samples. Okay.
Okay, thank you.
You're welcome.
Yeah, what does said the type of gases that you could sense with these zinc oxide nanorods? So what is the physics that
It's the gas sensing is like the sensors. It's like we use is a nanorod is a metal oxide. It's sensors. That's why it's sensitivity to the gas. Different gas humidity is a carbon dioxide and like that.
Okay, thank you. So, if there are no more questions in the room, so we move to the coffee break. So we now have 10 minutes for coffee, and we see in the next session.
Thank you so much.
Thank you again for the talk, and that's
I'm sorry. Yeah.
third session of the topologically protected spin textures, fundamentals and applications. So we have 2 invited speakers and 1 contributed speakers. So we had a small program change. So the first speaker will be Matthias Chloe, and he will be speaking about current-driven skyrmions. And I think I let you. It's
So firstly, let me thank the organizers, of course, Jan, for organizing this exciting session. Thanks to Stefania for swapping. That relaxes everyone in the room. All right, so I'm going to talk today not just about fundamentals, but really also about possible applications. And after some very brief introduction, because you all know what's going on, you're all super excited, I'm actually going to talk about applications to non-conventional logic. Everyone knows the racetrack. But I used to work for IBM. I sold all my shares in IBM, so I have no vested interest. But I also, since the last 15 years, every year I've been saying the racetrack is 5 years from market. And so I'm giving up on that now, so now we're going into non-conventional logic. But first, let's start. So what do we need in order to make skyrmions stable? And for that, we need a special interaction. So we all know the spin-spin-Heisenberg exchange interaction, which stabilizes spins parallel or anti-parallel. However, it doesn't care if the spins couple like this or like that or like that, so there is no predefined chirality. However, that's a problem because it means that these 2 types of domain walls, these 2 Niel domain walls with clockwise or counterclockwise rotation, have the same energy, and that means they can actually annihilate, and that means they're not homologically stabilized pairs of them. So what do we need in order to make one of these domain walls stable and the other one not? And for that, nature has something in store for us, which is the Janoshinsky-Maria interaction, which couples at the interface between a heavy metal and a ferromagnet 2 spins, not just parallel or anti-parallel, but actually perpendicular. And not just perpendicular in any direction, but only one perpendicular orientation. And that means that you have a fixed chirality when the spins can from left to right. So here we see a clockwise.
Yeah, now I think it works. Okay, great, thanks. So I'm not going to repeat everything, but for the online people, please read these 2 papers. They're amazing, and you'll learn everything about orbital currents and the orbital rush by Edelstein effect, and it gives you 16 times larger orbital torques, and everyone's happy. Okay, good. But now we want to move skyrmions with it. And so here is what the student that was working on that drew before he did the experiment. He put 4 skyrmions on a racetrack, inject currents, move everything, and then build a device. Now this is what it looks like in reality. We have 4 skyrmions. We're super happy. But when we inject current, we see that these 4 skyrmions, well, they kind of move, but they don't all do the same. And initially we start with 5 skyrmions, and then after some time we are left with 3 skyrmions, so we lost half of our data. So this is not good. So, IBM was not impressed. So the question is, why do the skyrmions not do all the same thing? Where does this pinning come from? So that's something which we spent quite some time investigating. And what we did is we looked at a sample, and we determined the energy landscape of a sample. And red spots are pinning sites, and black spots are areas where the sample never goes. So from this, we can actually determine the energy landscape. You see it's rough. It's not flat. So skyrmions like to sit in certain positions, and they are repelled from other positions. So we can calculate the energy landscape, and now we want to understand how a specific pinning site pins a skyrmion. So what is the origin of the pinning? And for that, what we did is we looked at the skyrmion here, and we see it doesn't randomly move, but it moves between certain positions where it likes to sit. And we then actually plot the circumference of the skyrmion for these different positions where it likes to sit. And then we see that the domain wall here for the black, for the red, for the green, or for the blue, the domain walls, they superimpose for large areas, meaning that there are areas where the domain wall likes to sit. And it turns out it is not the center of the skyrmion which is being pinned, it is the domain walls. And that's also something that we can understand because the domain wall is where the exchange energy is highest. So obviously, if the domain wall can lower its energy by sitting at a position where the DMI or the exchange is a bit lower, this will actually save it a lot of energy. So it turns out that we can actually understand the pinning of the skyrmions by the pinning of the domain walls. And that's kind of nice because this allows us also to tune the skyrmion size by pinning one end of the skyrmion and moving the other side of the domain wall a little bit. And this gives us a lot of flexibility for tuning the energy landscape of the skyrmion. If you're interested, the paper just came out a couple of weeks. Okay, and we also saw that the same is for a stripe domain, not just for a skyrmion. Also, the domain walls of the stripe domains like to sit in the same position where the domain walls of the skyrmions like to sit. Okay, good. So now, if we crank up the power, we can overcome pinning. And then we can get reproducible domain wall motion. This was shown already a few years ago, where we saw that the skyrmions can move reproducibly 10 billion times back and forth, and then IBM was happy again. The skyrmion velocity tracks the pulse shape very nicely. However, we also see that not just the skyrmions move along in the current flow direction, but also, and now I need to wait until the computer has decided to go to the next slide. That the current and the skyrmions don't move parallel, but under this so-called skyrmion Hall angle. And that was something that was investigated actually by the group of Axel Hoffmann and us at the same time. And we found that the skyrmion Hall angle, in contrast to theory, actually has a dependence on the velocity. Theory predicts it should just be flat, just depending on the size. But here it seems to change with the velocity. And we had experimentally similar results, but completely different theory. So in their work, the Charles Reichert family, Cynthia Reichert, they predicted it's due to pinning. We predicted it's due to spin structure deformations. And in the end, it turned out that both were right. Their theory holds in the creep regime. Our theory holds in the viscous flow regime. And then, meanwhile, there's quite a bit of literature on this, including a recent work that we did, where we showed that depending on the regime of the dynamics, the change of the skyrmion Hall angle with velocity actually has different slopes. All right, so now we can move the skyrmions in the racetrack, but the question is, of course, why has no one built a racetrack commercially? Well, there are many reasons. There's a big reason, and that is market. There's already pretty good memory out there, and you'd actually have to compete with that. So we went away from skyrmion racetrack and went to non-conventional computing using thermal dynamics. So your brain is a good object that uses thermal dynamics. So your brain operates at the very threshold at stability. Your brain has a lot of mistakes that happen all the time, and sometimes you see that with me. But so you have a lot of activity in your brain which is not deterministic, but it's stochastic because your brain doesn't want to use more energy than absolutely necessary. And so we will do the same. We use thermal diffusion, so dynamics of skyrmions in this multilayer here. And when we move it, we see that the skyrmions not only move in the current flow, but they also wiggle around. So this is a signature of Brownian motion dynamics, like a blue ink in water wiggles around. Here our skyrmions wiggle around. Now this was theoretically predicted to be wrong. So theory predicted here in this paper that this should not be observable. So we were a bit skeptical, but then I told the student, just switch off the current, switch off the field, and just observe. And this is what you see. The skyrmions don't sit still. They actually move around by Brownian motion, as you can see here. And this Brownian motion moves them randomly in this energy landscape. And if you then plot the mean square displacement as a function of time, it's completely linear, and that means it's diffusion. It's pure diffusion. So it's not super diffusive, it's not subdiffusive, but it's pure diffusion. And this was actually reproduced by Uli Novak. The paper came out a couple of years ago, and there's also some other work by our colleagues. But we got excited because when we started this work, and we said, well, forget about the racetrack because this diffusion is bad for the racetrack, our colleagues, Daniele Pinna, Karin Everscher-Sitte, they wrote theory papers about using this in stochastic and reservoir computing. And that's how we started. 3 years ago, I had no clue what all this stochastic, reservoir, neuromorphic, blah, blah is. I still don't have much of a clue, but I got more excited about it. So what can we do in order to make use of this thermal dynamics? So the first thing we need to have very fast thermal dynamics. And in order to get very fast thermal dynamics, we actually teamed up with Uli Novak on synthetic antiferromagnets. And we found that if you have a topologically trivial combination of two antiferromagnetically coupled skyrmions, they can move 10 times faster than ferromagnetic skyrmions. So actually we have a 20 times increase of the diffusion. And if you're interested, here is the paper on arXiv. If you're a referee, please be kind. So we can do very fast skyrmion dynamics due to random diffusion. But let's use it. So here let's start with non-conventional logic using skyrmions. So first we're going to use stochastic computing. So stochastic computing is a non-arithmetic way of calculation using random bit streams. It's an approximative approach, and it's a simple way of multiplying numbers, and you can do also scaled addition. But there's a problem, and that is the creation of unbiased, uncorrelated bit streams. Now this sounds very cryptic, so let me explain this to you. So if you have a coin, you flip the coin, you have 50% chance of heads and tails. If you have 4 cards, the chances of an ace is 25%. To encode the information of 0.5, we actually encode this in a bit stream where we have 50% ones and 50% zeros. So 010011110101001100 corresponds to 0.5. And 0.25, you have 25% ones and 75% zeros. So 0.0001000011 and so on, that corresponds to 0.25. So in a bit stream, we can actually encode any information between 0 and 1, any number between 0 and 1. So now we will use these 2 bit streams and feed them together in an AND gate. And then what we get out, 0 and 0 is 0, 1 and 0 is 0, 0, 0, 0, 0, 0, 1 and 1 is 1, and so on. Then we get a number out of this AND gate, and it turns out that the number we get out is actually the multiplication. So the bit stream that is coming out of the AND gate is actually the multiplication of 0.5 and 0.25. So 0.5 times 0.25 is 0.125. So the chances is 12.5% to have both heads and an ace. So this means if you have these bit streams, you can very efficiently generate a multiplication of the 2 numbers. Now what's the problem? The problem is the bit streams X and Y have to be uncorrelated. So let me show you what this means. So here we have a bit stream that corresponds to 6 over 8, 1, 1, 0, 1, 0, 1, 1, 1. So we have 6 over 8, meaning 6 ones and 2 zeros. Here we have a bit stream that corresponds to 1/2. We have 50% ones and 50% zeros. And if we do the AND gate, 1 and 1 is 1, 1 and 1 is 1, 0, we get this one here, which is 3 over 8. That's completely correct. Half of 6 over 8 is 3 over 8. Now, we put in two identical bit streams, so fully correlated. And 6 over 8 times 6 over 8 is not 6 over 8. So that's definitely wrong. So completely correlated input streams give you wrong results. And so now what we have to do is we need to shuffle around the order of the ones and zeros while keeping the number of ones and zeros constant. So to reshuffle the order of the ones and zeros to decorrelate these input streams. And there is no efficient, scalable, low-power solution for this using CMOS. And that's where we set in. We need a way to reshuffle the order of the ones and zeros while keeping the number of ones and zeros constant. Okay, and this is what we built. We built a reshuffler made of two chambers. Up here is a 1, down here is a 0. If we inject here a skirmion, it's a logic 1. If we inject here a skirmion, it's a logic 0. If the skirmion exits here, it's a logic 1. If the skirmion exits here, it's a logic 0. So we nucleate here with currents. We do readout by imaging or by TMR devices, and then we look at the input and output. And what we see is, so here skirmion enters is a logic 0, and here one enters a logic 0, here one enters a logic 0. Now one skirmion exits here, it's a logic 0. Another skirmion exits here, it's another logic 0. Now a skirmion exits here, it's a logic 1, and so on. So now we have here an input stream and here an output stream. And because the skirmions are actually not getting lost, they're topologically stabilized, this means that the number of ones entering here and exiting here is the same as the number of zeros entering here and exiting here. So there's no 1 and no 0 is lost, but because they move around here randomly, the order of which the skirmions enter here, exit here, exit here has changed. And you see the skirmion bit streams, input and output, look very different. And if you calculate the p-value change, it's negligible, meaning that all the skirmions that enter here, exit here, all the skirmions enter here, exit here, so no skirmion got lost, but the correlation is down to 11%. So that's really good. We've nearly completely decorrelated the input stream into an output stream while keeping the total number, i.e. the represented value, the same. And we, of course, tried to make the cover page of Nature Nanotechnology, and we failed, so you get to see this instead. And now you can feed these streams into an AND gate, and then you can have a probabilistic computing that does very efficient and very low power multiplication. And now in the last 3 minutes, let me show you another more recent approach, reservoir computing. The problem with these very nice stochastic computing is that we can only do very few operations very well. We can do multiplication and scaled addition, but it's not a general purpose computer. Reservoir computing is pretty exciting. Reservoir computing is something that for pattern recognition is a very topical area of research because it maps a complex problem into a linearly solvable one. So it comprises an input, a reservoir, and an output. And then the network that we use here does not need tuning, so the connections inside, they don't need tuning. We only tune the output. So there's no problem with training. And what it does, it projects, for instance, this ensemble of these blobs into a higher dimensional space where they can be easily be separated into these different classifications. And of course, there are different ways to realize this, and we have chosen skirmion fabrics. Actually, all the honor to George Buriano from Intel, who came up with this together with Karin Evershaw-Zitter. And here's a paper where we conceptually suggested that. So we have our input. They go as current into a skirmion lattice, and then, or a skirmion fabric, and then we have TMR output junctions. And now here is the simplest version of it. We have here our skirmion lattice, and we have 3 inputs, which can be put to plus, minus, or 0. And then we actually look at the position of our skirmions for different combinations of inputs, and we read out the skirmion in 4 different positions by, for instance, TMR junctions. And then as a first approach, we simply showed whether it can do Boolean logic. And we see, for instance, AND works very well, NAND works well, OR, NOR, XOR, and XNOR. And the interesting thing is that XNOR is actually a non-separable function, so that cannot be realized with a simple perceptron feed-forward network. So that's something that was very exciting because it allows us to actually outperform a simple perceptron just using a single skyrmion in our reservoir. If you're interested, the paper is coming out in a couple of weeks. All right, so this is the end of the presentation. Most importantly, this is the people that did the work before Corona, during Corona, and after Corona. And we have great collaborations at MIT, Konstanz, LBL, PSI, at the MPI in Stuttgart, in theory in Mainz, as well as our 3D Magic Consortium and Christian Gut in Siegen and colleagues in Sendai in Sydney. Nothing will work without funding, in particular the RST Synergy Grant. And then to summarize, DMI stabilizes chiral spin structures with a defined topology. We find that pinning is at domain walls. Here are the papers. Skyrmion motion can be obtained due to spin orbit, but in particular orbital torques. We get the Skyrmion Hall angle and very efficient dynamics. We get this thermally induced Skyrmion diffusion, in particular in synthetic antiferromagnets that can be used for probabilistic logic. And we've realized low-power reservoir computing. If you're interested, there are all the papers. If you're new to the field, there are some reviews. I'm very happy to share the slides, so if you don't want to write on all the references, send me an email. We also have open positions for PhD students and postdocs. And with that, I thank you for your attention.
Thank you, Matthias, for this comprehensive talk. Are there any question in the audience? Yes. One moment, please, for the microphone.
A second.
The Skyrmion Hall effect.
People live in real life, not just 2D. Yeah, go ahead.
I'm saying that the Skyrmion Hall effect created a problem in long propagation in the waveguide.
Yeah.
Was it possible to find a solution of the problem?
Yeah, I think there are two solutions that we at least are exploring. I mean, we saw one in the talk before using these anti-skyrmions and then choosing the right angle, but I think that's quite tough. So what we use is synthetic antiferromagnets. Synthetic antiferromagnets, you have two skyrmions which are coupled, and since they want to go in opposite directions but they're coupled, they go straight.
So the answer is antiferromagnetic skyrmion.
I think that's one answer. That's the one we are doing like right now. So synthetic antiferromagnetic skyrmions, yeah.
But do you believe in the future for the skyrmionic racetrack?
Is anyone recording this? I can tell, I said this in the beginning. When I left IBM, I sold all my shares in IBM, so I have no vested interest. That's all I can say about this.
Yeah, thanks, Matthias. For the reshuffling problem, so you need to conserve the skyrmions, but it's known that when you drive the skyrmions with current, sometimes it happens that they annihilate each other. So how do you control these in your devices?
Yes, it's a good question. I didn't talk about this in a lot of detail. So it turns out that in the skyrmion reshuffler, we find that they never annihilate. And the reason is that we have very little pinning sites. It's an optimized stack. And the skyrmions that we're annihilating, they only annihilate if they're pinned, because then they're not topologically stabilized anymore because DMI is low. So here, we find they play billiard. So they actually interact. If one goes close to the other, it is pushed away. And you see here, so the p-value change of 0 means that no skyrmion is lost. So we put like 10 to the 6 skyrmions, and 10 to the 6 skyrmions come out. So by engineering this, you can make it so stable that actually this problem of annihilation is not there. I mean, it's not so important anymore that the skyrmions actually get annihilated. So I think we can make them stable over years with no visible decay.
Okay, Kai.
Very nice talk, Matthias. For the pinning you mentioned, how much does that depend on the skyrmion size? Because the proportion of the domain wall will be different depending on the size, for example, right?
That was me. Okay, so the pinning depends very strongly on the skyrmion size, and we now have a paper on arXiv where we show that if we actually have an AC field excitation that changes the size of the skyrmion periodically, we can get rid of all the pinning. Because the pinning only works for a certain size. A certain pinning site only works a certain size. If you periodically change the size, as soon as the skirmion enters at a pinning position, already has changed its size, it's not pinned anymore.
Right.
And then it's fully diffusive and a flat energy landscape.
And this pinning is from whatever defects?
Yeah, it's a
in-
polycrystalline film, so we think it has to do with grain boundaries, because that kind of fits also the size. But it's, I mean, if for the students, if you want to make a huge impact, find out where the stupid pinning is coming from. It's a very tricky question, but it would be really good if you figured out. We don't know. We think it's grain boundaries where the DMI is changing.
Thank you.
I have a follow-up question to Saul, actually. When you showed this...
Can you go full screen again? I'm sorry, I pressed on the wrong button. Oh, wow. And now I crashed
Computer's
the
thinking.
computer.
Actually, yes. So here you are generating skirmions and you're moving them by injecting some current,
Yes.
I suppose.
Yeah.
So you are you rely on the fact that the skirmion will not be linear with the current, because otherwise you cannot generate that stochasticity.
Ah, yeah, okay. So the stochasticity comes from just thermal activation, and we can use extremely low current density of 10 to the 7 amps per square meter, because we have this additional thermal activation. And so indeed here there's a superposition of drift due to the current and diffusion due to random thermal activation.
Okay.
So this superposition means that eventually they move, but they don't move exactly with a predictable deterministic velocity. So that's why you have the reshuffling in this chamber here that leads to this order of the skirmions exiting being different from the order of the skirmions entering. So you have both a small current pushing it, but on top of that thermal activation that moves it in a random orientation.
But the operation will be very slow then.
Absolutely. So there's no free lunch. So low power typically comes with low performance. I mean, the application we have in mind is autonomous sensing, where you need very little logic, but you have very little power available. So we work with companies that do autonomous sensors, which rely on energy harvesting, and they only need a very simple gates, AND gate, OR gate, majority gate, and things like that, which we can use here. And they only need power, they only need performance where they need calculations in the hertz range. They don't need gigahertz. Like for a sensor, you're not going to read it out at gigahertz speed, but you're going to read it out once a minute. A CO2 sensor to see if people have enough oxygen, that's something you read out once a minute. So it can be very slow, but has to be very low power. So that's absolutely. So we don't try to compete with Intel on making Pentium processors.
Okay, thank you. Okay, is there any other question?
Yeah,
Yes.
sorry, just a quick curiosity. I didn't read your paper. So is that a synthetic antiferromagnet?
So this was actually shown in a normal ferromagnet, but
Because I don't see any skirmion Hall effect, so they seem to be all, on average, to go straight.
yes, because they're very large. So the skirmion Hall angle is 18 degrees or 13 degrees. It's very small. The skirmion Hall angle for these large skirmions is very small. That's why we don't see it. But in the other one, it doesn't matter. In the synthetic antiferromagnet, they go straight automatically, for free, and they go faster. So they're really good. But we just did that a couple of months ago, so that's why we're not there yet to do it also in devices. Hi.
Okay, thank you, Matthias. So we have to move on. So let's thank Matthias again. So the next speaker is Stefania Pizzini from CNRS, Institut France. And she's going to talk about current-driven domain wall dynamics in ferromagnetic manganese nitride films.
Thank you very much. Oops.
Is your microphone
Do you
on?
hear me? I don't know.
Can you?
Is it okay? I don't think it works, no? Sorry? Ah, okay. Let me just check if this works. How does it work? Ah, this is so forward. Okay. Okay, so I need to go back. Okay, hello everybody, and sorry for those who came to listen to to Matthias. I end up stuck with me, so it's a good opportunity to be here anyway. And thanks to Chan for giving me this opportunity. So today I'm going to talk about current-driven domain wall dynamics in ferromagnetic manganese nitride, and this is a collaboration between our group in Institut in Grenoble, SpinTech laboratory, and then the samples that I'm going to present were made in Tsukuba University in Japan. I was going to present you, where we come from. So since we are at the seaside, I'm going to show you some mountains. So we are in Grenoble, we are surrounded by mountains, and we are on this Polygon Scientifique, so we are close to European synchronous radiation, neutron facility, and we are at the CNRS Institut Niel, and we are close to our people from SpinTech that you might know better than Institut Niel. So this is to go down, sorry. Manganese nitride is one of the few known magnetic nitrides that are presented here. They are all grow in the antiperovskite structure. And we thought it could be interesting for spintronic applications because they are made of cheap, light, and abundant elements. They don't have any critical elements like cobalt, heavy metals, or rare earths. So in the bulk, manganese nitride grows, so it's a ferrimagnetic material with the two sublattices corresponding to what is called manganese 1 in the corner side, and with this large moment, and manganese 2 in the face-centered moment. The easy magnetic axis is in the 111 direction. It has pretty high nail temperature, and in the bulk is a non-collinear ferrimagnet. But we are interested in thin films. These thin films, as I said, they are made by our colleagues in Tsukuba University in Japan. They are made on, we studied once depositing strontium titanide, STO. Their typical thickness is of the order of 10 nanometers, and then they are covered with silicon oxide to prevent further oxidation. So these samples are made by molecular beam epitaxy. They have, because of the very small mismatch between the two crystal lattices, they are very nice. They have a very nice crystallographic structure, as seen here by TM measurements. So very good epitaxy with a very sharp interface and practically no dislocation. What about the magnetism? Yes, from the magnetic point of view, we find that the tensile stress gives rise to perpendicular anisotropy. So we have this 100 texture and also magnetic anisotropy. So what I forgot to say is that the magnetization is the net magnetization is parallel to the manganese 1, so perpendicular here. VSM squid measurement shows also out-of-frame magnetization with a very small, so it's a ferrimagnet with a very small magnetization. Just to give you an idea, 70 kiloohm per meter corresponds to more or less 15 times less than the magnetization of 1 nanometer of cobalt in the systems that we are used to. Large PMA, and just to make sure, so there is no magnetic compensation temperature because the evolution of the two manganese site is the same in temperature. And then we were surprised the first time that we put these thin films in our Kerr microscope, and we saw these huge domains, so they're like 1 millimeter size domains, which reveal that they are due to the good crystallinity, so the very small density of intrinsic defects. So as I say, it's a ferrimagnet, but no compensation. So what we asked our colleagues in Japan as if they could dope the samples with nickel or whatever and try to obtain this compensation. And this was done by doping with nickel. So they doped the samples with different concentration of nickel. So for me, X is the concentration in the formula units, so between 0 and 0.20. They managed to conserve very nice epitaxial growth, 001 orientation, and then these CDX measurements show that the nickel had a very nice distribution, a homogeneous distribution within the layer. So they're neutral, via XMCD measurements, they found out that the nickel was actually substituting the manganese 1, so this corner side, and their magnetic motion was antiparallel to the one of the manganese, so which means that by increasing the concentration of nickel, you can reduce the magnetization, and then it was expected based on what is known about what they measured about the neutron scattering measurements on bulk system. They found that they expected to have compensation for about, let's say, 20% of 20x6, so 0.18 in a formal unit. This was confirmed by the measurements of our colleagues in SpinTech by anomalous Hall effect. They showed that by increasing the concentration of nickel, they had a change of the sign of the anomalous Hall effect angle, which indicated that about 20% as predicted by the theory. Our VSM squid measurements also show that it should be around this concentration by 20%, where the compensation, concentration compensation was expected. Okay, so what about, the main talk is about the current-driven domain wall dynamics. So for this, our samples were patterned into strips. So these are 2 micron and 1 micron strips. These are Kerr measures, so differential Kerr images. So the contrast here that you see corresponds to the displacement of the domain wall driven by current pulse. And you can see here this contrast, so this length stays the same. So there are very small dispersion of the displacement of domain walls with the current. Also related to the fact that we have a crystalline system in which we have very small pinning of domain walls. So of course we change the current density, and this is the velocity, the domain wall velocity versus current density. So you can see, so we see this large, for those are, note this, okay. So we see this very large velocities of the order of 1,000 meters per second for 1 to the 12 amperes per square meter, and for those that are in that field, these measurements, these velocities are more or less of the same order of magnitude of the ones that are obtained by spin orbit torque in system with Jelinek-Moore interaction. But what was peculiar here and surprising is that the domain walls move parallel to the electron flow. So the question is, what is the mechanism that responsible for domain wall speed? Sorry. So as you may know, there are 2 phenomena that can be invoked. The classical spin transfer torque that was studied a long time ago. Actually, it was mainly studied in the years 2000, 2010, at the beginning of, let's say, when we started working on this system. So a long time ago, mainly on permalloy. At that time, so the domain wall velocities, the maximum velocity was about 100 meters per second. The domain walls move parallel to electron flow. I didn't say anything about the phenomenon. The current is spin polarized within the ferromagnet because of conservation of angular momentum. When the electron spins aligns parallel to the magnetization within the domain wall, a torque is exerted on the domain wall that moves the domain wall in the direction of the electron flow. So what, at the moment, let's say that recently there have been practically no measurements on samples in which the spin transfer torque was supposed to be the phenomenon that drive on domain walls, especially since up to now there are practically no effect in systems with perpendicular magnetic anisotropy. And why? So in the years 2000, people were concentrating on platinum cobalt multilayers in which there was no inversion of symmetry. And what was found out, for example, in platinum cobalt multilayers is that there was insufficient spin polarization to move domain walls. But as you probably all know, in the last 10 years or so, we have concentrated on samples in which cobalt or ferromagnetic layers are deposited on heavy metals, and so we have a spin orbit torque that moves domain walls that are stabilized, that have certain chirality stabilized by Jelinek-Moore interaction. Matthias has just talked about that. And in that case, what has been found is that the larger velocities are obtained in systems with, in ferromagnetic systems close to the angular compensation. And in that case, domain walls can move either in the direction of the electron flow or in direction of the current, because this direction depends on the size of two interactions. It depends on the sign of the DMI, so the chirality of domain walls, and on the sign of the spinel angle, so depending on platinum or tungsten on the heavy metal. So in our case, domain walls move, is it this one? Yes, no. Moves in direction of electron flow. So so we were convinced that it was the spin transfer torque is the phenomenon that drives the domain walls. But to completely exclude the presence of spin orbit torque, we also measured DMI in the system. So we did domain wall speed measurements driven by an out-of-plane field in the presence of an in-plane magnetic field. And we saw that the domain walls moved symmetrically in the presence of the magnetic field, and this completely excluded the presence of DMI, although we didn't necessarily expect DMI in this system because of the absence of heavy metal. So we concluded that domain walls are blocked in this system. So as I say, there is no spinel effect material. So we expect the domain walls to move in the direction of the electron flow. So the conclusion was the domain walls are driven by spin transfer torque, and this is the first demonstration of efficient spin transfer torque in a system with perpendicular magnetic anisotropy. If you take the 1D model for spin transfer torque driven domain wall motion, you see that so the efficiency is essentially driven by is given by the ratio between spin polarization and magnetization. So we have a system with a small magnetization because it's a ferrimagnet, and then by fitting this curve, we found out that the polarization was about 65%. So which explains why we have this large this large domain wall movement. But as I say, but when we dope these samples with nickel, then we can decrease further the magnetization and go towards the compensation. So let's see what happens when we increase the nickel doping. So this is the first sample in which, so the sample without doping, and this is again velocity versus versus current density. So now we start doping the sample, and I present here the velocity for this current density as a function of magnetization. So we go closer to the magnetic compensation. We keep doping the sample, and then so increasing the nickel compensation. And then once we cross the magnetic compensation, then we have a change of the direction of motion of the domain walls. And then, okay, we go further, and then we decrease again. So what are the main results of this study? The first one is that we have this huge domain wall velocity. So we get to 3 kilometers per second, so 300 meters per second for this this corresponds to about I think 18%, 0.18 of nickel doping, and then. So this is the first result, and the second is that the reversal of domain wall motion when we cross the magnetic compensation. To be noticed that if we take, for example, a system with platinum, gadolinium, cobalt, and it's driven by spin orbit torque, the domain wall direction does not change direction when we cross the compensation, because, as I say, it's the DMI sign and it's spinel effect sign that is not expected to change across the compensation. So it is really typical of this system. And then, okay, so we were happy to see these large velocities that are actually comparable or even larger than the fastest measured with Carnell was in ferromagnets driven by spinel torque. So if we wanted to, in order to explain these results, we considered the QFE model that was adapted to a ferromagnet close to angular compensation. So in general, with these parameters, So this model was developed in the case of a ferrimagnet, so an intermetallic, so gadolinium cobalt rare earth transition metal effects, in which the germinating ratio for the transition metal and the gadolinium are different, so you need to consider, so you will have that angular compensation point and the magnetic compensation will not the same, will be distinguished. So in our case, we consider the fact that the two magnetic sublattices are composed of the same metal. Therefore, we made the supposition that gamma 1 and gamma 2, so we suppose that the magnetic ratios are the same for the two sublattices. In this case, it means that the magnetic compensation and angular compensation point will be the same. So the velocity is given by this expression, and then you expect that the magnetization would, the domain wall velocity would be vanishing close to the angular compensation point. So we fitted this data with this, our data with this formula, and then, and this is the best fit that we could obtain. And there are three parameters: the spin polarization, the damping, and then beta, that is the adiabatic term for a spin transfer torque. And then you can see that we have this very small contribution of the adiabatic torque and this large magnetization. So this large polarization. So our conclusion was that the large spin transfer torque domain wall velocity can be related to the increase of the domain wall velocity close to the angular compensation and to the large spin polarization that is given here. And last thing to say is that according to the model, you have a vanishing magnetization, vanishing velocity at the angular compensation point. This point where in our fit the velocity is cancelling is the magnetic compensation. So this confirms the fact that our supposition, the gamma 1 and gamma 2, so not considering two different ferrogrammetric ratio was right. So I think I finished. How long do you have? Am I long? Okay, then it's fine. Okay, so the last discussion was about what about the change of domain wall direction. So in the model that was that I just discussed, the sign of the change of the domain wall direction is due to the fact that across the compensation you will have a different the reversal of is due to the change of the relative direction between the angular momentum and the spin polarization. And this was the case in if you take platinum, gadolinium, cobalt, the spin polarization belongs to the how do you say would be the cobalt that the ferromagnet that would be responsible for the spin polarization, and then the direction of the motion will change across the compensation where the magnetization changes sign. So in order to explain this, we will have to prove that the spin polarization does not change direction across the angular compensation, and for this we asked our colleagues from SpinTech to carry out band structure calculations, and what they showed is so they considered two systems, manganese nitride and manganese, so undoped and doped sample across the on the other side of the compensation. And what they found is, so these are the density of states at the Fermi level for manganese 1 and manganese 2. What they found out is that the majority carriers in the manganese 2 sublattice was carrying the spin polarization both above and below the compensation. So this proves that the spin polarization doesn't change sign as the nickel composition is increased, and this can explain our result. So the fact that the relative orientation of polarization and magnetization across the compensation explains the variation of the velocity, the domain wall velocity direction while crossing the compensation. So I think it's finished. Yeah, I just wanted to situate our results in the let's say, in the state-of-the-art results on the field. Up to now, so these are the results of the spin transfer torque from, let's say, the year 2010. We have the spin orbit torque driven domain wall speeds here with the maximum on the platinum gadolinium cobalt from the beach work, from the beach group. So they had a bit more than 1,000 meters per second, close to the compensation temperature in this system. Then we have all these results here are taken for, so they are garnets, so you can see these huge velocities for the magnetic garnets, but in this case, the magnetization, actually the domain wall, so these are spin orbit torque driven domain wall speeds. But in this system, the DMI is not strong enough to have nail walls, and so an in-plane field was applied in order to move the domain walls. So these are all in-plane magnetic field applied on top of the current. So let's say that our final message would be that spin transfer torque, although it seems to be an old subject, we can show that it's still interesting if you find a sample that have a low magnetization and a high spin polarization. Yes, and this is my conclusion. Thank you very much.
Okay, so thank you, Stefania, for sharing these wonderful results. Okay, questions? Yes, please. Microphone.
Yeah. Can we say that magnetic properties here in these materials are mainly determined by the large PMA? And the second question, did anybody try to do ferromagnetic resonance experiments on this material?
The second question, I don't know. I don't know because we are not doing that. But the first one is no, it's not a perpendicular magnetization. So the fact that perpendicular magnetization is there, of course, is interesting because domain walls are narrow and then you can move them fast. But no, the most important property is the fact that it's a ferrimagnet and with a low magnetization, and then especially close the compensation. Then we have, I mean, everything is just due to the fact that spin transfer torque is proportional to P, spin polarization, divided by MS. So it's really one, the large spin polarization, and two, the small magnetization. Then it's perpendicular, so it's another.
And what about ferromagnetic resonance?
I don't know. Sorry, we are not doing it, and our colleagues in SpinTech don't do it, and I'm not sure that. I think it has been tried by our colleagues in Japan, but I don't know. Yeah, I'm sorry.
But it's a natural thing to do.
Yeah, I know. Yes. But I think it was tried for try to obtain the alpha. In fact, I think it was done because they found yes. In fact,
as
it's
soon as you finish static.
Yes. They did it, and I think that they did it because we also needed the damping factor, and in fact, it turns out that they found the damping factor was 0.017, I think, and it corresponded to what we found from the fit of our data. Yeah. Yes.
Yeah, thank you for the talk. I'm not that familiar with this type of, spin transfer torque-driven domain wall motion. But if I remember correctly, you need block-type domain walls, and also you have a problem that the Walker breakdown limits at which velocity you can drive.
But that is the case for magnetic field-driven domain walls. That is the Walker breakdown is actually yes. But, because, there are two regimes. Here we are in a regime that is beyond the Walker breakdown. In fact, yes, because the breakdown in the systems is very, very low, because the Walker breakdown corresponds to the field in which you go up, you start, this is a precessional regime. We are already beyond the Walker breakdown. The Walker breakdown is determined by where you start, you kill the the demagnetizing energy of the domain walls, which is extremely small in the sample because AMS is practically zero. So this is beyond the Walker breakdown.
Okay, okay, thank you.
Yeah. Everything is in our first paper, Nanoletters 2020.
Okay, here.
Okay, thank you for the nice talk. My question is about the fitting. You use the Q5 model to fit the velocity against MS.
The second, the second one or the first one? I mean, with nickel or without nickel?
With nickel. When you change the saturation magnetization here, and you have three parameters here, you said. My question is whether these three parameters also fit the velocity against current linear response in the precessional regime, because it's the same parameters that enters the law, the mobility. I mean,
so you want to know if it's fitting?
I guess it's a nice,
yes,
but but you only fit these parameters in the other curve, and then you check that it works here.
No, but then it was done individually for each. Yes, of course.
Great.
Yes. I mean, that was taken just for one domain, for 1 to the 12. Yes, but it was fitting. Yes.
Any other question? Yes, Sabri.
So, thank you very much for the nice presentation. I wanted to ask a question about the second fit. For the spin torque coefficients, spin transfer torque coefficient for the polarization and non-adiposity. Yeah. So when I want to do micromagnet simulations, these are basically my inputs. But since you have the domain wall velocities for different systems, basically, because they have different dopings, I would somehow expect that this parameter should also then change for the system, so that they're not constant for the entire model, but to be depend on the doping ratio.
Yes, but you need to know that the doping ratio is extremely small. So even the maximum, the 20%, corresponds to 4% of doping.
Ah, okay.
So it's really nothing. So okay, you are right, but the concentration is very small. So. But also you can see that the fit is not perfect, but okay, the magnetic parameters really change very little. Yeah.
Okay. Thank you.
But it's a good question, of course. Yes.
Okay, let's thank Stefania again and move on. Okay, so we move to the last speaker of the session. So it's Mikhail Otrokov from Ijarbasque, Spain. And he's going to talk about point defects and their influence on the Dirac point gap at manganese bismuth telluride system.
Okay, thank you very much for the introduction, and good afternoon everyone, and welcome to my talk. Of course, the fit of this topic is not perfect to this session, but let's say this is due to I would prefer to speak like this because I have some voice problems, unfortunately, so you will not hear me. Okay. So, yeah, but let's say this is due to the program issues. Anyway, I will assume that you find the topic appealing and interesting. So, as you have probably noticed, I have changed the title of the talk slightly because I was allocated unexpectedly about 30 minutes for the contributed talk, which is just great. And I decided to cover this exciting topic in more details. I mean, the mystery of the Dirac point gap, not only the defect issue, but also just in a more broad sense. Okay, for those of you that are not very familiar with the topic, a brief introduction. Manganese bismuth telluride is the first intrinsic magnetic topological insulator. It's layered van der Waals material made of this septuple layer block, with manganese layer occupying the central layer of the block, and the neighboring blocks are connected by the van der Waals gaps. The magnetic structure is as follows. It's an interlayer antiferromagnetic ordering in which the ferromagnetic manganese planes are coupled antiferromagnetically along the z-axis, and the out-of-plane magnetization takes place. Because of the combination of these crystal and magnetic structures, the material meets the combined S-symmetry, which is the combination of the T1/2 translation, it's a fractional translation which connects neighboring manganese atoms from the adjacent manganese planes, and this is the time reversal symmetry operator. And this combined symmetry gives rise to the Z2 topological classification of antiferromagnetic insulators. And actually, if you perform the DFT calculation for this material, you will see that it is an insulator with an inverted bulk band gap due to spin-orbit coupling, and the Z2 topological invariant is non-trivial. So this is antiferromagnetic topological insulator, and this was confirmed experimentally in many publications. So actually wrong sequence of the slides. So it caused a lot of excitement, and actually quite soon after the discovery of the MBT, a huge family of materials was discovered, like this MBT, BT, MST, ST, natural superlattices. People were alloying this with antimony. There was this 225 stoichiometry and selenite version, and actually the properties are remarkable. For example, in 3 dimensions, they are not only antiferromagnetic TIs, they can also exhibit high-order topologies with hinge physics, for example, this Möbius insulator state or ferromagnetic axions. They can also be topological crystalline insulators, or Weil semimetals, or even harbor this Floquet Bloch state. In 2 dimensions, and this was confirmed experimentally, they are either antiferromagnetic axion insulators, or intrinsic quantum anomalous Hall, or ferromagnetic Chern insulator under, let's say, of course, ferromagnetic under external field, but without Landau levels. And if you employ a little bit of engineering, like twisting of the thin flakes, or doping, or heterostructuring, you can think about flat bands with high Chern number, high-order topological superconductivity, Majorana fermions, skyrmions, etc., etc. And last but not least, I would like to emphasize the capability of this family of materials of hosting a number of different Hall effects. Quite a few of them have already been confirmed or claimed to be confirmed in experiment. For example, this novel layer Hall effect. So actually, there are 2 more talks on MBT in this conference on Thursday. So I think they're worth attending. I hope you will inspire yourself. So directly to this topic of my talk. Of course, to confirm that this material is topological, you have to perform surface electronic structure measurements with ARPES, and this is what we report in our Nature paper 2019. You have this Dirac cone, which is gapped, as you can judge by the EDC, energy distribution curve representation of this photo emission data. This is below Néel temperature, which is 25K. And this is in agreement with theory. So everything looked quite okay, except of maybe the quite weak sensitivity of the topological surface state gap to temperature. But since many groups entered the business kind of instantly, there was a second wave of ARPES studies, now made largely with laser radiation, and they, as reported here, consistently claimed the vanishing or absent Dirac point gap in MBT with much higher quality of the photo emission data. And this came because, came completely unexpected, because it contradicts the theory, contradicts the initial experimental report. So nobody was understanding anything. This more fresh, let's say, ARPES study provides maybe more a complete picture of what is going on, but doesn't explain actually. But what is going on is here, for example, you have a statistics of 15 MBT samples grown by different groups. For example, this with triangle is one group, without triangle is a different group. And summarizing the results of all of the experimental evidence, we can claim that there is a sample-dependent situation in which the Dirac point gap seems to acquire an arbitrary value of about between a few and several tens of millielectron volts. So what was going on there? Of course, people came with a number of explanations of the phenomena. For example, in this first STM study of MBT, they did not actually find the Dirac point gap whatsoever, and therefore they suggested that maybe there is a magnetic dead layer on the surface of this material. On the other hand, these other 2 papers speculated that maybe the magnetization tilts and it is locked within the surface plane, or maybe even the manganese layer is antiferromagnetic completely, not ferromagnetic but antiferromagnetic. In this case, if you perform the calculations, of course you will have gapless Dirac cone, but actually there are strong experimental counter-arguments with respect to these suggestions, and they are as follows. A magnetic force microscopy evidences the persistence of the uniaxial antiferromagnetism at the surface of MBT. So the data look like this. These are the septopole layer high terraces, and the magnetization respects this A-type antiferromagnetic order. And on top of that, the XMCD measurements reveal the out-of-plane easy axis, so nothing weird change happens at the surface from the point of view of magnetism. So what about possible structural changes near the surface? Well, if you do a theoretical exercise of expanding the first van der Waals gap from the surface up to a huge value of about 15%, you will see that the gap vanishes. But nobody observed this in STM because it's quite straightforward. Everybody measures like 13.6, 13.7 angstroms, which is something in a good agreement with thickness of septopole layer with measured with X-ray diffraction. And if this was the case, you would measure something like 15 angstroms, but to the best of my knowledge, nobody did that. So this is not the case apparently. And actually the interesting result was reported in this publication where they experimentally observed a collapse of the MBT surface in the thin flakes. Of course, this might cause severe changes of the electronic structure and closing of the Dirac point gap at least. But actually it was only observed in the thin flakes exfoliated in the argon atmosphere and transferred in the argon atmosphere, and never the surface of the bulk single crystal. And I would like to emphasize that to the best of my knowledge, the all micro laser ARPES measurements were performed for single crystals in the ultra high vacuum. So this apparently not the case either. And finally, if you continue theoretizing of what may it be, you can imagine that, okay, maybe there are some near surface electric fields. For example, it is known that during ARPES you may have effects like photostimulated absorption and ionization, which was previously reported for non-magnetic topological insulators. And those could potentially create some uncompensated charge at the surface, and this is the effect of it. The Dirac point gap disappears. And of course there is a shift. I don't have much of a counter-argument against this, but at least there is no proof. No disproof either, but at least Dirac point, okay, Dirac cone does not, it doesn't seem that it shifts that much during the ARPES experiment. So just to summarize this discussion, as you remember, the laser ARPES provides very well resolved dispersion lines of MBT, which means that the surface quality is reasonably good. And this is in agreement with STM. Therefore, the surface septopole structure would be the same or largely the same as that in bulk. And therefore, since this is the van der Waals layered material, nothing is expected to happen with the surface magnetism. And this is actually confirmed by magnetic force microscopy. Thus, the Dirac point gap does not seem to, Dirac point gap issue or mystery does not seem to come from a radical change of the magnetism at the surface or some severe surface degradation not observed in the single crystals in vacuum. Actually, the only one experimentally confirmed and abundant imperfection of MBT is manganese bismuth intermixing, which could look like this. You take a certain fraction of manganese atoms from its layer and you substitute them by bismuth, and this half of this fraction of manganese goes here in the bismuth layer and the other half here. So manganese bismuth intermixing. Depending on the experimental technique you use to measure it, depending on the model that you use to fit experimental data, depending on the sample, maybe on the crystal growth approach, you may have, or at least there was a reported between 1 and 9% of manganese atoms per bismuth layer. And this is how they look like in the STM at relatively large scale. They look like they are many, but actually they are just 5%, maybe because they are triangles, they look like something more than 5. And this is how it looks like in a DFT simulation. And this is the only one firmly established and abundant structural imperfection of MBT. So the magnetic implications of this manganese-bismuth intermixing were discussed recently. Of course, neutron diffraction would be the perfect tool to establish what is going on there, but fortunately or unfortunately, there seemed to be not enough of this intermixing to let's say, make a solid conclusion based on neutrons. Apparently, there are no such data. In contrast to what happens with manganese antimony telluride, because their intermixing is much more pronounced and they have this well-established conclusion about the behavior. But anyway, they were indirect means to conclude what is going on there. For example, these high temperature, high magnetic field magnetization measurements, which provided us with the surprising result that the magnetic saturation of MBT takes place at a huge field of 50 Tesla. And the explanation of such a behavior was that due to cation intermixing, manganese atoms incorporated in the bismuth layers appear to have their magnetic moments coupled anti-parallel, they are pointing down here, with respect to the central manganese layer. And this apparently is the strongest the system. It takes like 50 Tesla to overcome it. So we asked ourselves whether these imperfections can have some effect on the Dirac point gap. So we performed this relatively simple illustrative, I would say, calculation. We have actually started with an analysis of the topological surface state charge distribution in the real space, and we have noticed that, of course, this is the distribution for the ideal material superimposed on the structure of with the intermixing. But anyway, you see that here in the manganese layer you have a lot of magnetization, but just a little of density of TSS, topological surface state, which actually mostly located here near the bismuth layer and especially here. So what we did is, of course, we have calculated the ideal case, 90 milli-electron volt Dirac point gap, and then what we considered is just we took these two layers. Okay, imagine that all the structure is ideal, but we just take layer number 2 and layer number 4, and we swapped 10% of manganese and bismuth, like a double defect. Bismuth here and manganese here, bismuth here. So what we found, and we imposed this antiferromagnetic coupling. And what we found is that the Dirac point gap decreases, but it is still sizable. But actually the topological surface state mostly located here. So we took these two layers and we kept all of the other layers intact and we swapped it once again. And this is what we've got. So it's gone. No, there is no Dirac point gap basically, because please note that this energy scale is much smaller than those two. Okay, so our initial interpretation was is that these manganese bismuth atoms act on the maximal density of states of the topological state and the real space, and since their magnetic moment is pointed anti-parallel with respect to the central rail, they are kind of competing and they are balancing one another. Actually, this explanation was challenged recently by the Bin-Hai Yang group, who have gone further. They considered various structural cases, and also they considered this ferromagnetic case fully polarized. This, of course, this is 50 Tesla, but anyway, hypothetic case in which manganese bismuth atom is coupled parallel to the central layer of the same septuple layer. And they have considered this ferromagnetic case, which is the ground. Okay, and I would like to emphasize that both in our calculation, only the topmost septuple layer contains this manganese bismuth intermixing. So what they get is that in this A-type AFM and this ferry AFM case, the gap decreases, basically the same what we found. But the explanation that they give is different, and this is in the next slide. And in this case, the good news, in ferromagnetic case, no gap decrease. Okay, so what they find is in the cases where the gap decreases, actually in both cases, ferromagnetic, antiferromagnetic case, the topological surface state charge density, this orange line here and here, it displaces downwards, so it escapes from the surface. And basically, here you have once again a competition of the two blocks that are magnetized in the opposite directions. But here, there is no competition. They both contribute, let's say, constructively, and the gap stays large, while here it kind of shrinks. But actually, here I would like to emphasize that in our and in their case, only topmost septopolary contain defects. So I'm not sure that topological surface state would go down if all of the slab would be defected, let's say. But I understand that it is difficult to do this in the supercell calculation, so we have to go beyond that and find more adequate ways to describe it. But anyway, both studies point towards the defects origin Dirac point gap. What about the experiment? Actually, there was not much until but this recent PNAS paper by Liu and co-workers, they have been able to show for the molecular beam epitaxy MBT films that in the regions where you have quite, let's say, with a little incidence of these manganese bismuth defects, you have the gap in the STS with which they attribute to the Dirac point gap. Actually, it is gone when you go higher than the Néel temperature. But in these highly defected regions, you have the decrease of the Dirac point gap or even disappearance, which kind of confirms the previous theoretical suggestion. And I would also like to highlight this recent data obtained by Felix Lübke and co-authors on the single crystals of manganese bismuth antimony telluride. There you have much more pronounced intermixing because antimony and manganese, they have closer ionic radii, so there is a lot of intermixing. Okay, much more than in the pure MBT case. And they have this Dirac point gap fluctuation across the surface, nicely visualized here. So the average size is about 30 millielectronvolts, which you can probably resolve in the laser RPS. And the largest value is about 60, a few places actually, and and then it goes down basically to 0. This is kind of what I would expect based on this data as well for MBT, but not so pronounced. And actually, it's kind of funny because 7 years later, with these next generation topological insulators, intrinsic topological insulators, magnetic, so we have arrived to the same result that was published by Siamos Davis group back in 2015. You remember, maybe, they published basically this image for chromium-doped bismuth antimony telluride. With this, I don't want to say that MBT and derivatives are useless, but of course we have to address this severe problem of manganese bismuth intermixing. So with this, I'm coming to the end of my talk. I'd like to thank my collaborators, both theoreticians and experimentalists. And yeah, these are the take-home messages. The gapless Dirac in MBT is likely due to intermixing between manganese and bismuth, and suppressing this intermixing could likely resolve this Dirac point gap issue and enhance the quantum anomalous Hall effect observation in MBT, which is currently about 1.4 kelvins, as well as increase the temperature of the quantum Hall effect without Landau levels, which is currently about 20, 30 kelvins, depending on the group and publication. And yeah, I'd like to thank you for your kind attention.
Okay, thank you, Mikhail, for this very nice talk. So, other questions, Juan?
So thank you for the talk. So I'm not a fully expert on this system, but so what I get is very, so I think that it's very complicated to control this topological insulator. And for instance, if I am right, so for instance, it's 1.4 Kelvin quantum anomalous Hall effect, but it's not robust because you have to apply magnetic field. There is no quantization at 0 magnetic field in this system.
There is, but probably 1.4 is the highest. You don't have to apply an external magnetic field according to the report in Science by Chinese group. but they were the only group that reported that. So in theory, it should be quite straightforward that you observe in the, let's say if you have an odd number of septuple layer block, you have a non-zero magnetization.
Yes.
Because they go like this, like 1, 2, 3, right?
Yeah.
But probably due to this intermixing, it was difficult to realize this quantization without field. With magnetic field, there is a number of experiments, like I don't know, maybe there are 10 or more experiments that confirm this, precisely this quantum Hall effect under field, but without Landau levels, which is due to topology of the material.
Okay, thank you.
There's a question on the back side of the room.
So this manganese bismuth anti-side defect is atomic-like defect. Then, to which extent, the lateral extent, it affects so the Dirac gap? Because imagine, so the beam, the photon beam in an ARPAS experiment, the aperture is much larger, so it's somehow some microns. So it covers the area on the surface which has this defect, but also those areas which do not have. And that should give rise to some broadening of the node of the Dirac gap. Is it observed in the experiment or not?
Okay, yeah. The best laser beam that was used for the system, I think it's about 5 microns.
Exactly.
The terraces, maybe they are about micrometer size, but you don't know where you are shining. From the STM point of view, of course, you cannot cover that large area like systematically and count how the concentration fluctuates like from here to there, because they're like, I don't know, 1 micron apart. Our collaborators from Madrid, from Rodolfo Miranda group, they estimated that in the samples that they measured, the concentration was changing, as far as I remember, between 3.5 to like 5.2, and these are the second layer defects because the deeper defects are not very well resolved. Like there is another bismuth layer, but it is not seen. So, but I have just shown this, and unfortunately, there is no scale here. We can check it later on. This is STM data, I don't know, 30 per 30 nanometers or less. So this is how it fluctuates according to colleagues. And yeah, I hope this may answer your question. Thanks.
Okay, any other question? Okay, if that's not the case, so let's thank Mikhail again. And yeah, so you go to lunchtime now.
speaker will be Saul Velez. I don't know if I say the name properly. And he will talk about current-driven dynamics of nail walls and skirmings in an insulator. Thank you very much.
Thank you for the introduction, and I would like to thank Chan and the organizers for inviting me to present my work here in this very nice conference, a very nice place in Turkey. So today I will show you how we can stabilize chiral nail domain walls and skirmions in magnetic insulators and drive them by proximity electric currents applied to a platinum layer that is coupled to the magnetic insulator. So this work that I will show you today was done at ETH, and now I'm working in my lab in the Autonomous University of Madrid. So the motivation. So basically, one motivation was to work from two-dimensional time memory devices to the third dimension, in which essentially we are now able to drive these domain walls and magnetic domains in a track, so we can essentially now store information in the 3 dimensions. But beyond that, there's also the possibility to enable new spin logic applications and also new computational schemes, as this morning, for instance, Matthias Chloe was discussing. So, but how we can actually drive these domain walls or magnetic textures in a magnetic layer. So essentially, we are going to work with this kind of bilayer structures, which are stabilizing nail-type domain walls. And now, with these materials, so the essential ingredients that we need to have here to make this device to work is we need perpendicular magnetic anisotropies. We would like to have magnetic domains, stable domains, being out of plane. And we would like to stabilize these chiral domain walls, and we will do so by Jones-Cameron interaction, which is essentially brought by the proximity with a material with a strong spin-orbit coupling. In this case, it's platinum, that we use to stabilize one chirality of the domain walls. And this is also important because now we can also use the spin-orbit coupling of this platinum layer to generate spin currents, and these spin currents are coupled to the magnetization of the magnetic overlayer. And now we can control either the magnetic state we will have, for instance, switching, or drive the domain walls. As the domain walls have the same chirality and for the symmetry of the torques, what's happening here is that essentially all domain walls will move in the same direction. Now, if you run current in different polarities, you can drive the domain walls back and forth. But the questions are, now what are the limitations of the current device structures? And essentially, when you have ferromagnets, you have stray fields. Now the velocities that you can attain with this are limited, the high current density regime, but you can overcome this limitation via, for instance, working with synthetic antiferromagnets or working with ferrimagnets close to the angular momentum compensation temperature. Essentially what you see here is that when the temperature is away from the angular momentum compensation, the system becomes more ferromagnetic-like and saturates the velocity this density current regime. But now you can see that when the ferromagnet is compensated, the angular momentum is compensated, you can get higher velocities for the same current density. So, but as you see here also, we cannot drive domain walls in this regime of current density. So that's one of the main problems nowadays in these metal-based device structures, in which essentially are mostly polycrystalline. You have a lot of defects, and this limits the velocity of domain walls. Essentially are pinned in this current regime, and you would like to work in this current regime to avoid, for instance, joule heating, destroying your devices. That could be one possibility. So to overcome this, our approach was to use magnetic insulators, and in particular we are going to work with garnets, but there are many materials that also exhibit low damping. We would like to have as minimal possible dissipation in the system, also the dynamics, so that the small damping also favors the mobility of the magnetic structures in the system. And also these materials are known to, you can bring new functionalities to the system. For instance, you can excite spin waves that transport spin information via electric currents, or also very important is that most of these materials exhibit antiferromagnetic-like order. They are either ferrimagnet or antiferromagnet, and we are interested in particular ferrimagnets because we are able to measure the magnetic moment easily. But next step would be, for instance, moving towards antiferromagnets like you could work with hematite. So what has been done so far, you can, for instance, as I was saying, you can enable new functionality with these devices. You can excite spin waves via electric currents in a platinum layer, and now detect these electrically as well in second platinum layer, just placed away from the injector. And these materials, for instance, most experiments in magnetic insulator spintronics were done with yttrium iron garnet, which is typically in plane and very soft. But when you work with perpendicular magnetic anisotropy systems, as the ones that we are now interested, has been shown by Chan that you can excite, you can couple very efficiently by torques to the thulium iron garnet in this case, and you can switch the out-of-plane magnetization by electric pulses. So now the question was whether we can actually make racetrack-like memory with these materials now by applying electric currents also to the platinum layer. So the samples that we grow were on thulium iron garnet with perpendicular magnetic anisotropy by strain on scandium-specific gadolinium gallium garnet substrates, and we in situ grow platinum on top, and then we go to the clean room. We pattern this platinum layer in the type of racetrack-like device with Hall contacts. And now what we can do is to characterize the magnetic properties of the films by, for instance, measuring the resistance, the Hall-like response. And you see that there is a switching at this particular magnetic field. So you see a square-like response when you sweep the magnetic field out of plane. And this tells us that we have a robust perpendicular magnetic anisotropy. That is what we are aiming for these magnetic layers. So now if you apply a magnetic field in plane, you break the symmetry in the system by the symmetry of the spin orbit torques. When you apply this in-plane field, you can set the final state that you will get, and this is the demonstration. So essentially, when you apply electric current, the pulse, a negative current, so you stabilize down magnetization, but now if you switch the polarity, you can stabilize that magnetization. Now you reverse the direction of the in-plane field, and you reverse the opposite final state, and this is just the result of the symmetry of the torques. This tells that when we apply a current and the magnetic field are parallel, so we can stabilize that magnetization, or when they are antiparallel, we stabilize down magnetization. This allows us to set what is the final state, and this would be useful for magnetic memory-like applications. But we're interested on also seeing how these domain walls are moving. But first of all, we wanted to see how, because if you remember, we were measuring here now Hall resistance. We were just looking at switching in this region, but we are not sensitive to the wall track. But now what we did was to do polar Moog magnetometry. So essentially, you see here the differential Moog image with reference down magnetized state. Now when you apply a current in the current line, you see that the switching occurs only in the region that you have the platinum, and that's because of the torques. And this tells us that we can locally control in a continuous film, because the platinum layer was the only one that was etched in this case, and the thulium iron garnet is continuous. So this tells us that we can locally control the magnetization in a magnetic insulator. So now we're interested on seeing what type of domain walls we have in this system. So we have to remember that this thulium iron garnet is a center-symmetric material, and we would expect to have block-like domain walls. So now we implement nitrogen vacancy magnetometry that is based on a nitrogen vacancy in diamond. It is basically now setting or tip, and now scan this tip over the surface, and we can map the stray fields emanating from the main wall that is now in this case partially intersecting a region covered with platinum. So we now then, it's exactly this stray field map. And we now can track the stray field in different regions. So here in this region, we don't have platinum. Now we see that the stray field that we get is corresponding to the left-handed Nel chirality. So this tells us that now we only have tulimar and garnet. We don't have platinum on top. We don't have in principle any material with strong spin-orbit coupling, but we still stabilize on the left Nel type domain wall that is, in this case, brought by the DMI from the interface with the substrate, so the scandium, the gadolinium, gallium garnet. If we now put the platinum on top, we have a partial quenching of the left type Nel domain wall, and we get a partial block light type domain walls. And this essentially because the negative DMI that is brought by the substrate is now quenched by the positive DMI that is brought by the top platinum layer. So this is also consistent with different works, for instance, Professor Young or Professor Beach at MIT. And essentially you have observed the same in different substrates and also contribution from positive DMI of a platinum overlay. So next thing was to see how these domain walls would move. And we take one, so here is the track. So we have a domain already built up here, and we now run a current to drive this domain wall, and we can, by measuring just the distance that this domain wall is traveling, so we can extract the velocity, and we apply a magnetic field in plane to set the chirality of the domain wall. So because we have small DMI, we can help with the in-plane field to set the chirality of the domain wall. That's why we have here an increase of the velocity with the magnetic field. But now if you reverse the direction of the field and the current, so you can still move the domain wall from left to right, because now we are reversing the chirality and reversing the direction of the current, so we still move in the same direction, but the velocity is a bit different. This difference comes from the DMI that we saw that we were almost compensating from the bottom and the top the top interface, but we still have a certain DMI left in the system that is favoring a left type Nel domain wall that is schematized here, and now with external field we are either favoring the chirality set by the DMI, or we are opposing and setting the opposite chirality as you see here. As a result, the velocity is a bit different from depending on the direction of the field and the current. So this tells us that we can control the motion of the domain walls by controlling the direction of the current, the magnetic field in plane, and the DMI. And now there are also different works that show that you can even stabilize Nel-type domain walls, as Shan demonstrated, that you can stabilize at zero field with appropriate interfaces, and essentially you can drive also the domain walls at quite high velocities, even in the absence of in-plane field. So you can now also see what is the minimum current density that you require to drive the domain walls. And as if we remember that from the previous plots, so in this region you don't move typically domain walls in conventional metallic systems such as cobalt or cobalt iron boron, etc. You can see mobilities that are comparable to the ones or even larger that you would get with conventional metallic layers. So now that we know that we have that we can drive domain walls quite fast, and we have DMI in this system and so on, so now we wanted to move to the next step and try to stabilize the skyrmions in these systems. So what are skyrmions? As briefly, so essentially we have uncontinuous fields of the magnetic moment that carry topological charge. We know that this can be stabilized by DMI, so we have DMI in the system, and essentially what is important here is that with ferrimagnets you would expect to have much more compact skyrmions because of the absence of stray fields, and in ferrimagnets, the tulimar and garnet, you would expect to have as small as a few tens of nanometers at most. So the question is, now you can enable also this memory-like racetracks that we have with domain walls, but you can also make new computational schemes based on skirmions, which are nowadays the direction that people is moving. So the question is whether we can actually stabilize these skirmions in these magnetic insulators, and our approach was to couple the tulim iron garnet with yttrium iron garnet. And this yttrium iron garnet is in plane, tulim iron garnet is out of plane, and with this yttrium iron garnet we reduce the magnetic anisotropy in the system, and by this we favor the creation of more domains because we are reducing the energy required to generate domain walls, and by this eventually you would get skirmions in the system. So this is the steady cycle that you get for the tulim iron garnet. You see it's not now like a square-like thing, but more a bit softer perpendicular magnetic anisotropy. So now if you see that at different points here, so the type of domains you get, so here the contrast is not the best, but you can see kind of labyrinthic-like domains in this field-induced reversal of the magnetization, essentially induced domain, kind of labyrinthic-like type domains in the tulim iron garnet. So here we are only sensitive to the tulim iron garnet, and the jig is supposed to be demagnetized. So now, in these points here, what we do is to run a current. So you remember here we have platinum on top. Now what we do is to run a current pulse and see what's happening to these different states that we get along this the magnetization branch here. And when we are close to saturation and we apply a current pulse, we get kind of bubbles, small bubbles, in the range of 1 micrometer in diameter, and as you can see here, and also in this region you can see how these stripe-like domains break and generate bubbles. So for a better view here, you can see in this region, so this is a 10 Oersted, so it's in a region that you have kind of field track with domains. You can see both bubbles and stripe domains here, and essentially what I'm showing here is that you apply a current, so positive current, so drives the domains, all the domains from left to right, and here you drive from right to left. So you have repulsion in the system because they are, it's quite packed, but you can control the direction of motion of all domains, and this tells us that we must have right-handed Nell domain walls, and the chirality is just known because we know which is the sign of the torques that we expect with the platinum being on top of the tulim iron garnet. So by this we just infer that we must have right-handed Nell domain walls, but we can also confirm this by performing hydrogen vacancy magnetometry measurements of bubbles, isolated bubbles in this case, and here are experimental data for two types of bubbles. So this circular-like one and this one deformed by pinning. This tells us that we have some deformations also of the bubbles because we have some pinning centers in the system, and we assume that we have an elliptic-like shape. So that's just an assumption to fit this data. And the most important part is that from the fittings, we can infer what is the type of chirality that you get for the domain wall, because essentially this bubble is like a fat bubble and surrounded by Nell-type domain wall. And from this, from the fitting, we infer that it must be also right-handed Nell, as consistent with the direction of motion of the bubbles, and because these are closed domain by a Nell-type domain wall, this has a skyrmionic texture, so it is equivalent in topological terms as a skyrmion, and that's why we call this a skyrmion bubble. And then if you have skyrmion bubble has topological charge, it must exhibit the skyrmion Hall effect. That's what we measure, so we change the polarity of the core by the magnetic field. So with this, we change the topological charge. Now what we see is that when we run a current positive, so we drive the skyrmions from left to right, and the transverse deflection changes sign according to the polarity of the bubble, so the topological charge that the bubble has. And We can also characterize this for different combinations of direction of the current, topological charge, and so on. And we see that for all cases we have quite large Skyrmion-Hall angle. And the Skyrmion-Hall angle is large for two reasons. One is that we have small Gilbert damping. So you have to remember that here we have a ferrimagnet, and this large deflection angle is expected because you have small damping. This enables also to get quite large deflection angles even in almost compensated ferromagnetic systems. And also if you see here when you get to the depinning, so you don't have a progressive increase of the deflection angle, and this almost goes directly to the saturation velocity, to the saturation angle corresponding to the flow regime because you have low pinning in the system. So that's how you have low density of pinning centers. That's what we conclude from these measurements, the reason why we jump here quickly. But still, when you look at the trajectories of the Skyrmions here, I'm plotting several tens of trajectories in the system. You see that all the bubbles move in the same direction, but also has some bubbling around. And this is also because of the diffusion that we would expect to have in this system, because it has low damping, as for instance the samples that was discussing this morning Matthias Chloe. Essentially you can see here, you can also make better statistics of the motion of these Skyrmions. Now you track what is the individual displacements that you get here. So each point here corresponds to the position of a bubble after one pulse. And you can now make statistics, and you can see that you have essentially two distributions, one that corresponds to bubbles not moving, and the other one that corresponds to the bubbles moving. So these bubbles has a center that tells us this is the medium displacement that you get for pulse that goes in the direction set by the Skyrmion-Hall effect. But you also have a broad distribution that we to attribute to the large diffusion that you would expect to have in this system. So now you can also see what is the center with displacement you get as a function of the pulse length. And what you see is that large current pulses, you could see kind of a linear increase of the displacement as expected. But when you go to the short pulse regime, you get a saturation of this displacement, which we attribute to the pinning, the average distance between pinning centers in the system. And the last thing that we did, because now you remember we had YIG that we can also set in all the experiments shown so far were for YIG demagnetized. Now, so these are the trajectories for YIG demagnetized. Now if we control the direction of the YIG, and in particular we put it perpendicular to the direction of the current line, so the current line here, now we can control the motion of these Skyrmions. And essentially for this configuration of the YIG magnetization, you can see that the dynamics of the Skyrmions are more efficient than you get for YIG demagnetized. And when you reverse the polarity of the YIG, you get a much more block system that bubbles get pinned much more quickly, and essentially is much more difficult to drive the Skyrmions. And the simple explanation for that is that essentially when we have the yttrium iron garnet, we are distorting the texture of the Skyrmion. Now when we run a current pulse, we also induce a distortion over this Skyrmion. And if this distortion adds up, basically we are distorting much more than the system. And now the efficiency of the torques is much less in this case than for this case in which the magnetic texture is kind of the original one. So you require this yttrium iron garnet to see the effect of this distortion of the torques, which essentially you have in all experiments. But now because you have the YIG, you can see the difference between the direction of the current. And this tells us that we can control by magnetic exchange and torques, we can control the motion of the Skyrmions and also applies for domain walls. So if you have a straight domain wall, you have exactly the same effect. And finally, we exploit this, this control of the motion of the skyrmions by the spin orbit torques and the magnetic exchange at the region where we have almost the depinning current. And now what you see is that if we apply current pulses in this case, so we see that the skyrmions only move for one polarity of the current, so basically for this polarity of the current and this jig magnetization. Now we are driving the skyrmions towards the right direction along the current, but if we reverse the direction of the current, we don't have any motion, and we can restore the motion afterwards by reversing again the direction of the current. So we can see exactly the same if we now invert the direction of the magnetization and so on. We have exactly the same physics if we change the polarity of the skyrmions. So we know that we can control skyrmion motion in the system, and this behaves like a ratchet. So only in one direction the skyrmions are moving, and you can exploit this effect. For instance, if you have an AC current excitation, you would still have only one direction for skyrmion motion. And with this, I would like to conclude just summarizing the main results. So essentially what I've shown here today is that we can stabilize Snell-Chiral domain walls in magnetic insulators with perpendicular magnetic anisotropy. We can, in certain conditions, we can even stabilize skyrmions and drive both skyrmions and domain walls by electric currents. And finally, I've shown you that we can control also the motion of the skyrmions and also applies to domain walls by magnetic exchange coupling when we drive the skyrmions by spin orbit torques. And with this, I would like to thank all the people that have contributed to this work. And as said, most work was done at DTH, in collaboration with Kristen Dagen Group, which contributed with the nitrogen vacancy magnetometry, films growth, and spin orbit torques like related experiments, and also Sandra, which contributed with experiments on the skyrmions. And with this, I would like to thank you for your attention, and you have students that are interested in a postdoc or a PhD, so I will be happy to receive some calls. And thank you for your attention.
Thank you very much. Are there any questions?
Thank you very much for the very nice presentation. People usually also use these garnets for the spin waves, as you said, and there it's very important to have a very low damping. Do you know how does your damping change when you have this YIG and TMIG basically on top?
Yeah, we have, we don't have measurements of the ferromagnetic resonance measurements, we couldn't do that, but we infer that the yttrium iron garnet should in principle help to even reduce a bit more the damping that you have for the thulium iron garnet. This has been shown in different bilayers in which the damping expected should be in the range of 1 per 10 to the minus 2. And then we plug this, we take this number and we try to fit with the data that we observe, and it's consistent with this 10 to the minus 2. But we did not have these measurements in these very same films.
Thank you.
Thank you for an interesting talk. So I just have curiosity. Did you try to maybe just are the effect of, for example, Joule heating or Ørsted field in your case, or did you estimate these contributions?
Yeah. In the last part with the skyrmion motion, we did measurements of the temperature that we increased during the pulse. So we know that we always work with with an increased maximum of 10 degrees Celsius from the base temperature. And actually, well, maybe it's a bit difficult to find here, but I need to go to the second part. So I can show you measurements. So yeah, these are the measurements that we have. So here you see during the pulse, so we measure, we track the resistance in the platinum layer. So here you can see the change in the resistance. So this is a corresponding change in temperature. And we always work in this regime. So below 20 degrees Celsius temperature increase. And this corresponds to also in this flow regime. So we basically work in this regime of current densities and pulse lengths. We could not go to very high current densities because the Joule heating was too much, and then the bubbles start moving too quickly. We also know that we expect to have large diffusion in the system, and this large diffusion should drive very random motion of the skirmings is expected when you just increase by a few tens of degrees. And then Ørsted fields, we also have measurements of the Ørsted fields, and we can promote switching in one side of the skirming. So actually, maybe I can show you some image that also shows that you, maybe I think forward. Yeah, I think this one shows that here you see that you have a lot of bubbles in this region, also these bubbles, and these are reversed. So one is black and the other are right. And this is because you have Ørsted fields favoring from up and down domains and the sides. But we work always in the region that we can control that this is minimized.
Thank you for the interesting talk. You mentioned that pinning influences the trajectories of the bubbles, and this is due to pinning effects. Do you observe this at small currents, at large currents, or it doesn't depend on the current?
So we observe in all experiments because we cannot go to very high current density, so we cannot get to the flow regime. So we are working in the creep regime, and then we see effects of the pinning at all current densities that we were able to drive the skirmings.
But do you have any other indication that this is a creep regime, or it's just that you don't reach linearity in a sense?
We could not perform a systematic current density dependence and so on to make the fittings corresponding to the creep regime, because we don't have a large set of parameters that we can actually work with. But we know from nitrogen vacancy magnetometry measurements that we have deformations. We also, from the MOOC measurements, we could also track what the type of deformations we get and so on. And we expect these deformations to be already indicative of strong pinning of the bubbles in the domain wall of the bubbles and so on. But yeah, more experiments.
Thank you.
Okay, thanks, Saul. A question about your measurement of demagnetized YIG and magnetized YIG. So how do you make sure that the YIG is demagnetized, and do you have any idea of the domain size in the YIG, and would it correlate with the pinnings?
Yeah. The thing is, we always see random, so that the same type of trajectories we always see when we are supposed to be demagnetized. What I can tell you is that when we saturate the YIG in the perpendicular direction, so along the current, for instance, that's here. So in this configuration, you will not expect to see the ratchet effect. And now what you do is to apply the magnetic field parallel to the current. So there must not be asymmetry between positive or negative current, and we see more or less similar motion. So this tells us that we are saturating the YIG. At least this tells that we have actually control of the YIG magnetization. We are now working with the same magnetic fields that we apply for the other experiments that were showing this ratchet effect. And we believe that the YIG domains are probably quite small because we cannot see at the size of the skirming, we cannot see the effect of the YIG or the YIG domains or some domain walls that you may have in the YIG changing the trajectories of the skirmings. So that's what we infer, but we cannot measure directly the domain structure that we have in the YIG.
you measure as grown, or you do so when it's demagnetized? So how do you make, like, what do you do to tell that it's demagnetized? So is it as grown, or is it?
Okay. So you can characterize here with magnetometry. So this is with a magnetic field applied in the plane, and this is the hysteresis that you get for the magnetic response for in the plane, and this is the YIG response. So this is the jump that you get, and actually with less than 2 Ørsted, you already kind of saturate the YIG magnetization, or at least you get a lot of domains in this direction, and here you are already.
So at 0 feet, you assume that it's demagnetized.
Yeah. So we are working here in this, around 0.
Actually, I had exactly the same question. So the relationship between the pinning and maybe the pinning by the domain was in the YIG, so, but you already answered. So I think we should pass to the next speaker.
Thank you.
Thank you very much. So the next speaker is Kai Liu. Wait. Yes, Kai Liu from Georgetown University, and he's going to talk about pulling magnetic skyrmions out of the thin air. I don't know what it means, but we will see.
Yes, thank you, Stephanie. First of all, I'd like to thank John and other organizers for this opportunity to share with you some of our recent work. It's actually part of our recent effort with magnetoionics, so I'll give a brief introduction. There are actually quite a few experts here. Then I'll mostly focus on efforts using chemisorption approach to induce DMI and chirality switching. And I also discuss some recent effort showing the palladium capping layer induced effects. And then if there's time, I'll briefly touch upon some potentials for 3D information storage. And for this expert audience, I don't have to spend much time. There's been so much effort trying to use electric field to control magnetism in order to address, among other things, the energy challenge in nanoelectronics. And typically, the electronic effects are most dominant. The ionic effect has been highlighted particularly over the past couple of decades in memristors, where the electrical resistance depends on the prior history. And this may be because of conducting filament formation and breaking, or ion or vacancy migration. And interestingly, if you design the system right, you can have ultra-fast switching below nanosecond. And there's already been interesting applications in artificial neural networks. The magnetic version can be traced to the seminal work by Dominique Givort's group that uses electrolyte to gate under this electric field. There's charge accumulation on the exterior surface of the material, which induces electrostatically another layer of the opposite charge. So you have this electric double layer near the surface. And this modifies the carrier concentration and the material properties, such as anisotropy. And there has been a number of excellent review articles here. So what we have been mostly interested in recently is the solid-state version of this magnetoionics, which in essence is really atomic scale control of the interfaces. And this can happen either electrostatically, which is limited to the interface, or electrochemically, where you transform the interface into some, oops, I pressed something wrong. Can we restart this? Yeah, thank you. And with electrochemical means, you can change or transform the interface into something completely different. And this have led to many exciting results. For example, in this seminal work from Jeff Beach's group and also Wei-Gang Wang's group, that they show the perpendicular anisotropy at this cobalt gallium oxide interface can be toggled. And this is consistent with prior studies that shows the oxygen content right at this interface. The cobalt-oxygen bond plays a very important role to PMA. And the effect size actually can be very large, which is very useful. And then recently, we've done some study looking at the interfacial electrochemical reaction where using gadolinium iron, a ferrimagnet, and the gadolinium is a very strong oxygen absorber. it grabs oxygen away from this interfacial nickel cobalt oxide layer, and it leads to actually a magnetic metallic nickel cobalt layer, which modifies the exchange bias effect. Importantly, this shows the effect can go well beyond the interface. And in fact, since the earlier days of magnetic ionics, there's been so much progress in the field, including many efforts by experts here. There have been so much magnetic functionalities that have been demonstrated. In fact, in principle, you can modulate all magnetic functionalities using this handle, and you can do so energy efficiently. And they are also compatible for 3D integration. So I will focus on our recent effort in trying to use this effect to explore DMI, which again doesn't need much introduction here. And typically the DMI is fixed once you make the material, once you design your layer stack, especially for the interfacial case. Then this DMI is fixed, introduced into the system. And some of the pioneering work has been shown here by Professor Vincent Dunger's group. And what we are interested in doing is to use, in a controlled ultra-high vacuum system, try to use chemical absorption to explore induced DMI, which gives additional handle to introduce topology into the system. The technique we use for imaging the spin texture is spin polarized low energy electron microscopy, which uses spin-dependent electron reflectivity to capture the magnetic contrast. It can also image magnetization vector with a very high spatial resolution, approaching 10 nanometer. And some of the earlier work has been shown in this prior publication. And this one, in fact, shows our interest in exploring DMI in light element system, in contrast to a conventional system that involves heavy metal because of the strong spin orbit coupling. So for our study, which is led by Dr. Gong Chen, we first came up with a background. It's kind of like when we do X-ray diffraction, we want to use a zero plate so we know clearly what the peaks are. Here we want a background that has essentially zero DMI, which is this multi-layer structure of nickel cobalt, which gave us the perpendicular magnetization, and then palladium tungsten have opposite DMI. So if we design the thickness of the palladium just right, we can cancel them out, which is shown here. This is the case with 2.1 monolayer of palladium, and then this is the SPLIM image. The black area shows the magnetization coming out of the screen, gray is going into the screen, and then along the domain wall boundary, the arrow shows the magnetization. And in this case, we see the magnetization are all pointing from black to gray, which is illustrated here. So they form this clockwise right-handed chiral near wall. If we increase the palladium thickness to 2.9 monolayer, we see the exact opposite. Now you see the magnetization is all pointing from gray to black. And this corresponds to this counterclockwise winding or left-handed chiral near wall. And in between at 2.46 monolayer, we have this two DMI balanced. So this is our zero DMI point. So we're going to sit very close to this DMI, zero DMI point. And we're going to sit initially on this side with a little bit larger palladium thickness. And so at 2.76 monolayer, we see initially the contrast. This is a SPLIM video. As we introduce oxygen, this is less than 1 monolayer of oxygen, we see the contrast going to change. Initially it was white here, black on top. As we introduce oxygen, the contrast switches. And this is more clearly shown here. Initially, we have left-handed anneal. Arrows are pointing from gray to black. And then after we introduce less than quarter monolayer of oxygen, we see this exactly switches. So the domain wall has switched from left-handed anneal to right-handed anneal. And this is a frame-by-frame breakdown. As we increase the oxygen coverage, we see this transition. We can also quantify this transition by monitoring this angle, which is the angle magnetization makes with respect to domain wall normal. At low oxygen coverage, we see a single peak indicating left-handed anneal. And eventually, as we increase the oxygen coverage, we see a right-handed anneal. And in between, there's the 0 DMI point. And this depends on the palladium thickness, because in this example, we start with 2.76 monolayer. If we have different palladium thickness, then it requires different amount of oxygen coverage to trigger this transition. And from there, we can actually construct this phase diagram that shows in order to balance the DMI change caused by 0.37 monolayer of palladium, we need about a quarter monolayer of oxygen. And from there, we can extract the DMI value, which is about 0.6 millielectron volt per atom for a single monolayer coverage. And this is actually quite large effect. Here, for consistency, we show the DMI value all determined by this spleen technique. And the oxygen chemisorption induced DMI is quite large. The physical mechanism here is the charge transfer because of the electronegativity difference between oxygen and the nickel. And so the charge transfer leads to a polarization and rehybridization, and it leads to an induced electric surface dipole moment. This is also reflected in the electron work function measurement, which we did. So with this large DMI, we're able to actually manipulate spin texture. Here is a skyrmion bubble, initially, on top of 2.6 monolayer of palladium. As we introduce oxygen, it goes from initially left-handed to achiral and then eventually right-handed skyrmion. And this is all done just at room temperature with oxygen. In this particular system, there's a little bit of a weak residual uniaxial anisotropy. So we've also looked at another system without the palladium, getting rid of this anisotropy, and we see this transition from chiral neo to chiral block. So this indicates the chemisorption-induced effect is actually quite useful to allow us to manipulate the spin texture. And then more recent study is then we go to the lightest element, hydrogen. In this case, we again use the same platform of a nickel, cobalt, palladium, tungsten. We sit very close to the 0 DMI point. As we introduce hydrogen, we again can induce this chirality transition from left-handed anneal to right-handed anneal. And this video would show this switching from black to white contrast, indicating this chirality switching. And we were able to trace this together with the electron work function change, which tells us the coverage of hydrogen on top of this multi-layer surface. And then we did multiple cycles. We introduced hydrogen, then pump it away, introduce, pump it away, and this is largely reversible. So this is actually quite relevant to, for example, solid-state ionic devices where you can introduce oxygen or hydrogen to the all-important interface into contact with the ferromagnet, and then you let this DMI handle to tailor the spin texture, and which I'll give some other examples later. So those two previous examples are all sitting near the 0 DMI tipping point. So as we use chemisorption to induce DMI, we're able to switch to the other side. Now, this example, we go to another tipping point. So this time, we still use the same stack, but now the palladium thickness is much larger. It's a 4 monolayer. So we're far away from the 0 DMI point. We're at another transition point, which is the spin reorientation transition. And by choosing the nickel thickness just right, as we introduce hydrogen, we can go from perpendicular to in-plane. So you see this video, when the contrast fade away, that's where the magnetization goes in-plane. Okay? And in fact, this is the same physics as Jeff Beach's group have shown in their proton pump experiment of solid-state magnetoionics, except there everything happened under buried interfaces. And in our case, we have a controlled platform to explore this chemisorption-induced effect. And there has been previous surface science studies shows that the hydrogen getting into contact with the cobalt surface would induce such a transition. So now, together with this anisotropy change, we found we can actually write skyrmions. This is a region in the S-grown film. As we introduce hydrogen, we observe what appear initially look like a bubble domain. But with using SPLIN, we can actually experimentally determine this Arrows-Array plot, and this is actually a new skyrmion. Okay, so this is all done just by introducing hydrogen. And this is an example of several different regions with magnetization pointing up or down, and then during several cycles. So this video hopefully will show. As we introduce hydrogen, we'll see the skyrmions nucleate, and then when we pump hydrogen away, they disappear. And we can repeat this multiple times. And so this is what I mean by pulling skyrmions out of thin air. In this case, it's the thin hydrogen. It doesn't have anything else. In contrast to the usual experimental conditions where you will need to use a magnetic field or electric field or heat and so on. But here we don't have any of that. This is an interesting new angle. And but it's not surprising really, because we're sitting right near the magnetization, the anisotropy transition point. So this effectively is changing the anisotropy, and we've done Monte Carlo simulations to confirm this. It's effectively like you're applying a magnetic field to tailor the local energy landscape, and you're able to write and delete magnetic skyrmions. In the next part, I will mention another recent study we did, again led by Gong, which is using palladium capping layer to influence the domain wall chirality. And this is looking at the same multi-layer stack of nickel cobalt on top of a palladium tungsten, down to about 0.22 monolayer. We are able to switch the domain wall from left-handed anneal to right-handed anneal. And then furthermore, using this, we're able to tailor the skyrmion bubble chirality. So this is a skyrmion bubble, and as we increase the palladium capping layer thickness, we see the topological character evolve. Okay, so initially this is a left-handed skyrmion. As we cap it with a thicker and thicker palladium, up to 0.22 monolayer, eventually switches to right-handed. But in between, you see this evolution starts to get a little messy, particularly at 0.14, 0.16 monolayer. And if we take a walk along this boundary, when it is a skyrmion, you finish a walk. Oops, sorry, I pressed the wrong button again. If you could please show it in slide mode again. For a skyrmion, if I finish walk along this circumference, I'm going to cover 2 pi, which will correspond to skyrmion number 1. And this is indeed the case for most of the coverage, except the 2 I mentioned earlier, that for the intermediate coverage of 0.14 and 0.16 monolayer, it goes back to 0. So these 2 cases are topologically trivial. And this is the part where right at the 0 DMI tipping point where the topological protection breaks down. And we can look at the DMI energy cost on both sides, which is actually very small. This for the size of our skyrmion, which is about a micron or so. This energy cost comes down to less than 1 attojoule, which is promising because this corresponds to the minimum energy we have to pay in order to switch it. But once you switch it, you can increase the thermal stability, kind of a borrowed idea of a hammer, heat-assisted magnetic recording, for example. So you can just tune very close to that switching point, spend little energy, switch the chirality, and then later on you can use other stimulus to boost up that thermal stability. Okay, so in the last bit, I want to mention some potential applications, as this figure has been shown multiple times. One of the envisioned application is using chiral domain walls or skyrmions for 3D racetrack memory. And in fact, Parkin's group just recently had another Nature nanotechnology paper experimentally realizing such a thing. Very exciting. One of the challenge is, of course, when you have such a complex 3D system, and it will be almost impossible to try to electrically control each individual spin texture. So this is where the chemisorption angle could come very handy, because that in principle offers a contactless way to allow us to switch the chirality. As we have already shown, we can switch the domain wall chirality with hydrogen chemisorption. And as you do so, you can influence the motion of such chiral spin textures. And in our controlled experiment, the chemisorption happens under UHV, but this can be readily integrated into solid-state devices. For example, you can use external stimulus such as the electric field to drive the ions in an ionic reservoir layer, drive it into contact with a ferromagnetic layer, and then at this interface, you can let this chemisorption to play its trick to influence DMI, to influence anisotropy, and so on and so forth. So we are pretty excited that this potentially can be integrated in the solid-state devices. And in that end, we've started some exploration of some prototype 3D structures, try to see if eventually we can get there, but this is still just the beginning. And one of our recent effort is to construct interconnected 3D magnetic nanowire networks. And the nanowire networks were built by using multiple angle ion tracking. So we use a radioactive source, and the decay fragments go through a polycarbonate membrane, and we do the ion tracking at multiple angles. And afterwards, we etch out the damaged tracks. We use electrode deposition to fill up the pores. So we end up with this interconnected self-supporting network. And we've made a number of different types, and I will focus on one type that's made of a magnetic cobalt, where we track the membrane at 3 angles. So one normal, and then 2 at 45 degree, at 0 and 180 azimuthal angle. So in order to study the magnetic behavior of such network, which is very complicated, we used something called a fork, first order reversal curve method. And this may or may not be familiar to the audience. I'll just mention very briefly. So instead of measuring a conventional single major loop, this fork method measures many partial hysteresis curves. We call first order reversal curve or fork. And then afterwards, we do a second order derivative of the magnetization with respect to reversal field and applied field. And in essence, we are basically disturbing the system to see how it will respond. We can get a distribution of this fork distribution, which illustrate the variations of magnetic properties in the system. So in simple cases, if everything is identical, let's say a collection of identical magnetic nanoparticles, you're going to see a delta function. And if you have a coercivity distribution but non-interacting, you see a horizontal ridge. If you have 0 coercivity distribution but finite interaction, you will see a vertical ridge. If you have both of this, then you will see a wishbone structure. And this were all experimentally observed in various systems. And so in our nanowire network, we see a lot of rich features. By the way, this is a mini fork library we built on our group website, which contains various, actually many systems addressing the different features of the fork technique. So using this, we were able to capture the magnetic fingerprints of the nanowire networks. This is the simplest case where the nanowires are not intersecting. These are just a single angle tracked parallel cobalt nanowire array. And we see feature, for example, this vertical ridge come from demagnetizing dipolar interaction because the adjacent wires want to be anti-parallel. And then when we vary the angle, we see eventually, for example, in this case, the magnetic field is perpendicular to all of the nanowires. We see a reversible ridge. Then when we go to the intersecting nanowire network, we see something similar but different. So in this case, this vertical ridge is still there, but now it's tilted, and then we see this wishbone structure. And this is because of this intersections, and it suppresses the demagnetizing dipolar interaction. And eventually, this case is where the dipolar interaction is minimal. So I won't go into details, but just to show you this qualitative difference. And in the end, we captured this fingerprints at all these different geometries. One of the interesting potential is that we can set the magnetic state of such a network in a particular configuration, and then we can use, say, magnetic field or current to drive that magnetic state to propagate from one region to another, which will be very interesting for potential 3D information storage. And to that end, we've done some initial study. We've measured magnetoresistance in such a network, and we did a magnetoresistance fork. Basically, the way it's done is we bring the network to saturation, we measure the magnetoresistance to a particular reversal field, then we go back up, then go to more negative field. So we see very interesting switching behavior. We have hysteretic behavior. Certain jumps only happen after we apply the field beyond some other jumps. So basically, only certain segment of the nanowire network has switched, then it leads to a subsequent switching event. There's also some stochasticity. Even though we start at the same field, sometimes it chooses a different path to switch back and forth. So these are some potentials to implement multi-state memristors. So with that, let me summarize. We've shown a number of magneto-ionic functionalities, particularly by controlling DMI and magnetic anisotropy, which allow us to manipulate skyrmions and chiral domain walls. And then there are some potentials for 3D magnetic nanowire networks. Then finally, the people who really did the work, much of the work I discussed were led by Gong Chen, along with Tritaman Bhattacharya and my other students, my colleague Geng Ying at Georgetown, former student Peter Mary and Mac Roberts, current student Mac Robertson, still at UC Davis, my great collaborators, Andreas Schmidt's group at LBL, Professor Roland Wiesendanger's group at Hamburg, Stefan Bluger's group at Jülich, who did the DFT calculations, Alex Groot, Julie Borcher's group at NIST for neutron study, Xixiang Zhang's group at KAUST for imaging, along with other colleagues at the Complutense, Autonoma University of Madrid, Nanjing, and Guangxi University. With that, I'll stop here. Thank you very much for your attention.
Thank you very much for your beautiful talk.
Thank you.
So I was wondering, when you put oxygen or hydrogen to the material and then you change the temperature, does this affect the material properties, so your skyrmions go away, your domain walls?
We did a temperature-dependent study on the hydrogen one. At a higher temperature, it's faster for the hydrogen to desorb. So that affects the kinetics of that desorption part. The oxygen one, I don't think we've done the temperature variation. But temperature certainly plays a role in this particular experimental setting.
Thank you. And I have another question.
Yes.
So did you also study then the dynamics? Because when you start switching the chirality, maybe in the meantime you go from Neal to Bloch-like, and then sometimes the dynamics are dependent on the helicity?
That's a great question. That's something we want to do. We have done very limited studies so far. We were trying to resolve first of all, the speed limit of the switching, and that's the thing we've been working on. So for example, the writing part of the skyrmion, the time resolution is below the experimental capability. So we know it's below 250 milliseconds. The desorption takes a few minutes because we're just pumping it away out of the UHV system. We want to do more as you're suggesting, and I hope to maybe report back later when we have more results.
Thank you.
Great questions. Thank you.
Very nice work. Thank you.
Thank you.
Just a small question about this palladium capping results, where you
Yes.
change the between left-handed and right-handed chirality.
Yes.
Is it pure right-handed chirality, or you still have block points or something? Because I don't understand the color code there.
Okay, yeah. So by the time we get to 0.22 monoliter, it's pure right-handed. It's at the intermediate state where we have a mixture. Oops. I have one chart. This one. Okay. So this earlier ones, these are all pure. This one, we really have a mixture. Yeah, you see this going, you begin to have block components. And this is where it breaks down, this two particularly. Yeah.
Okay, thanks.
Yeah, so some of this, it begins to develop some block component then, but it recovers. So if you follow this walk, it goes back to this 2 pi. But it's this intermediate stage that's the worst.
Thank you for the very nice presentation. So I have two short questions.
Yes.
First of all, so for the writing and deleting of the skyrmions,
Yes.
so you showed us this nice movie. So when you introduce the hydrogen gas, then you can write them, right? You can write them,
Yep.
and then when you take, when there is no gas there, then they disappear.
Yes.
But can you then just write them so they also stay there? Is there a way to manipulate in such a way that you can, or do you have to just keep on the gas? Or?
Yeah, in this case, yes, you sort of have to keep the hydrogen there to maintain the skyrmion. Once we pump it away, it goes away. Yeah, but to answer your question, if I were to think of a potential device in the future, maybe that's where I will nucleate skyrmion first, and then I will use some other stimulus, use temperature, magnetic field, whatever, to keep it. Then I can remove the hydrogen, will still be there, hopefully.
Okay, so thank you. And the second question regarding the 3D nanostructures. So can you then basically fabricate arbitrary shapes, or does it have to behave like, I don't know, do you have some constraints?
For this
can you also, like, so you have like stacked layers, you know, it's not only like one type or stuff like that?
That's very difficult. That's, I think, in general,
I know, that's what I'm asking.
for all this 3D nanostructure. This is basically allowed by our experimental setup, so we made such an interconnecting network. We can make some variations of it. We've made actually random networks of nanowires. But to have ordered structure layer stacked up, that's very difficult. Okay. Yeah.
Thank you.
Okay. I just have to ask two. The first one, what is the mechanism by which if you chemisorb hydrogen, you decrease the PMA? Because
The PMA. So this is, there was a study by Andreas Schmidt and co-workers in that, I think it was a PRB paper. The electronic structure modified, so there was a sign change for the anisotropy.
Because it seems a huge effect just if it's just electronics, but yeah. Okay.
Let me point out, let me see.
Yeah, it's this one.
Yeah, so for example, this PRB discussed, they really looked into the electronic structure when you have hydrogen on top of a cobalt. And then there was a sign change that made the PMA want to go in plane.
So it's just electronic effect, okay. But I don't know what is the change of the PMA. I mean, the actual quantitative change of PMA. You are close to the reorientation transition here.
Yeah,
anyway.
yeah. So I think this paper they have some figures showing the redistributed wave function. there was, I remember the sign change for the PMA. That's the reason for that.
And the second question is sort of a textbook question. Because, okay, from textbook we learned that DMI is supposed to be an interfacial effect. And then you show that, in fact, by changing the thickness of the palladium, so you manage to counteract the DMI that comes from the bottom. So it means that it's not an interface effect. So how do you comment about this?
Oh, that's a great question. I think there are both. Maybe we need a series to answer this, but we definitely see the effect from both interface and the bulk. In certain systems, maybe it's more sensitive at the interface. In others, definitely the bulk also plays a role.
Anyway,
so,
there are some
yeah,
papers by Google that show that actually it is not totally an interface effect.
Yeah, I won't be surprised.
But I just wanted to ask you the question.
Yeah, we in fact have done studies by tuning the layer thickness. We can definitely tune.
No, but it's very nice.
Yes. Yeah.
Okay, I think we can move on.
Thank you.
So you have your beautiful certificate.
Oh.
And so, where am I? So the next speaker, I think it's online. Yeah. Is yes, it's Lucas. I suppose he's waiting for us.
Yes, I'm online if you can hear me.
Sorry, we are a few minutes late, but don't make it serious. And well, we just wait for him. Yeah, because I just okay. Hello, Lucas.
Hello, can you hear me?
Can you hear us?
Yes, I can hear you.
Okay.
Can you hear me?
We hear you. Yes. So.
Okay, great.
Thanks for being there. So today you are going to talk about manipulating excitation in manganese oxide, and thank you very much.
Thanks for the introduction. I apologize and I regret that I cannot be there in person, but hopefully this is still as fruitful for everybody. I'm still very excited to show you some of our recent results. So today I'll be discussing how we can manipulate different kinds of magnetic excitations in oxide materials. And this is really a team effort. So what you're looking at here, the work you'll be seeing is from a variety of different places. These are the people that actually did the work. You'll see some work from my time at MIT, my time at Berkeley, in collaboration with groups and industry across the world. Currently, I'm an assistant professor. I just started a group at Brown University. So the data you'll see is from both my postdoc and my PhD. And so what do I actually mean by magnetic excitations? Well, as was very nicely introduced already in this session, I'm discussing things like non-collinear textures, such as domain walls, which can be chiral in some cases, things like two-dimensional bubbles or topological systems like skyrmions, even more elementary excitations, things like magnons or spin waves. And what you'll find is what we're very interested in and what excites us is really the ability to manipulate or stimulate these kinds of excitations to control their propagation and to control their dynamics. And so what I'll show you today is work where we can manipulate these different types of excitations, particularly in oxide materials. And the reason we're interested in oxide materials is because we can exploit some novel functionalities that these materials have. So things like correlated phenomena, non-trivial band structures, and really importantly, the ability to control these materials very, very precisely using atomically precise growth techniques. So this will allow us to uncover some new physics, a lot of which I'll talk about today, things like chirality, ultra-fast dynamics, and the effects of interfaces in these systems. And what you'll see is we basically have a two-pronged approach for attacking this materials physics and this science. And that's by using advanced growth techniques. So you'll see materials grown by pulse laser deposition and off-axis sputtering, as well as combining that with in situ characterization techniques. So what you see today is a lot of in situ imaging techniques and electronic measurement techniques. So with that, here's the outline for the talk today. I'll try to get away with telling you two different stories about two different oxide materials. One of them is a garnet oxide material, a historically widely used system that was already introduced earlier in the session. And I'll also talk about a perovskite oxide system, which is a correlated system. And through these two materials, I'll show you how we can actually excite dynamics so fast that we see relativistic effects, as well as the ability to control magnon propagation just by using electric fields. And of course, this underlying theme of using both synthesis and in situ characterization to access this physics will be highlighted throughout. So I'll first start off with this first story about garnet oxides. I don't think I need to motivate this very much, so I'll go pretty quickly. The previous presenters did this quite well. But as a reminder, most data on Earth is actually stored magnetically using magnetic materials, either through magnetic tape, which is a still hot area of research, as well as hard disk drives. So if you look at something like an IBM data center, such as the cloud here, you'll find that the majority of the data is actually stored on hard disk drives, where if you zoom in on platters or disks, you'll find billions, if not trillions, of magnetic grains or bits, where the magnetization state of one or a group of these bits constitutes a 1 or 0 bit of information. Now, this has been the predominant storage method for quite a long time. In fact, it's really withstood the test of time for a number of reasons, but mainly because it's very inexpensive to make these materials, and you can get very, very dense memories and data storage out of them. So these bits are on the order of 10 nanometers in size or so. However, what's perhaps obvious is the inherent limitations of this technology, such as the inherently slow read-write times. Because this device is mechanical, it's also not very robust. So the field, as has been explained already, has been shifting towards going from something where you have a hard disk drive, where you have physical, discrete bits that physically move the system, to something more solid state, where you have a continuous magnetic media, where you have different regions, or what we call domains, of uniform magnetization separated by finite regions or transition regions between these domains called domain walls, or these are non-collinear textures. And so if you can stimulate or drive these non-collinear textures into motion, you can effectively move bits back around. This has also been conceptualized not just in using 1D non-collinear textures, but actually 2D non-collinear textures as well, using things like bubbles and skyrmions. So this kind of begs the question, so how do you actually manipulate these magnetic textures? Well, the most popular way to do so today is using spin-orbit torques. And I'll just remind you, this is a way where in heavy metals, 5D transition metal oxides, topological insulators, and other large spin-orbit coupled systems, and even some magnetic materials, you can pass a charge current in these materials, and these the spins of the different charges actually get separated or sorted depending on their orientation. And so effectively, you can take a charge current and turn it into a transverse spin current, which has angular momentum. This is more easily seen by the cross-section here. And so this is a more efficient process than using something like a spin transfer torque. So essentially, if you place one of these materials, these spin to charge converters next to a magnetic system, you can actually take this charge current and drive a torque into the magnetic material. And the beauty of this is not only its efficiency, but you can actually apply this sort of spin-orbit torque to a larger array of materials. So things like magnetic insulators, which we'll look at today, and antiferromagnets, which we'll also look at in today's talk. And this has been demonstrated. We've known this, of course, for over a decade. It's been used to both drive domain walls and switch the magnetization of different types of magnetic materials. So the canonical system that's used predominantly today to study domain wall dynamics is an all-metallic system. It's based essentially on elemental magnetic systems, where you essentially have a thin bilayer of platinum or some other heavy metal coupled to a ferromagnet that's once again usually elemental in nature. And so this structure is actually quite useful. It gives rise to many effects such as PMA, which is needed for scalability, and also stabilizes the correct type of domain wall that's needed to drive motion in domain wall. It stabilizes an AL type from the Dzyaushinsky-Maria interaction. And this is important because these types of spin-orbit torques, these traditional spin-orbit torques for materials like platinum, really only act on domain walls with some Néel character. So the strength of the torque is a function of the domain wall angle. And so this device works pretty well. These material systems work okay. So here I'm plotting the domain wall velocity as a function of current density we're applying through the spin-orbit torque creating layer. What you'll find is that you can achieve domain wall velocities that are on order of a few hundred meters per second, which seems reasonably fast. But if you take a closer look, what you'll find is if you model this data, you'll see that there's a linear regime where the domain wall responds linearly to the current. This kind of makes sense. The more current you pass through the platinum, spins that are generated, and the torque that's exerted. But there's also a plateau regime which actually limits the domain wall velocity. This is fundamental to ferromagnetic materials. And it's really this plateau or the saturation effect that's kind of limited the propagation speeds of domain walls for a number of years. So where does this plateau actually come from? It actually comes from the domain wall structure itself, or what the magnetization looks like within the domain wall. In fact, when you drive a domain wall with a spin-orbit torque, not only do you drive it into motion, but you also distort that domain wall towards a block configuration, essentially away from the Néel configuration, which absorbs the torque. So it's not the static structure of the domain wall that's important, it's actually the dynamic structure of the domain wall that's causing this plateau. So luckily, a few years ago, our group, as well as a few others, discovered that just by changing the magnetic material system you're using to something that's more compensated, like a ferrimagnet with multiple magnetic sublattices, you can overcome this. So one common example is to use a rare earth transition metal alloy, where you can easily control things like net magnetization and the net angular momentum of the system by tuning things like temperature and composition. So what it turns out is these equations of motion, or this model, actually fundamentally changes when you use these types of materials. You can account for the net magnetization and the net angular momentum in these expressions up above, ferromagnet, and adapt them. What you find is what's actually important is the angular momentum. If you have a system that's completely compensated, meaning that it has no net spin, what you'll find is that the equations of motion in this domain wall change quite dramatically. So instead of having a linear regime and a saturation regime, in fact, you just have a linear regime. The velocity is always proportional to the current. You always get linear dynamics. And in fact, we've proved this. So using a completely compensated gadolinium cobalt system, we've achieved purely linear dynamics. Not only that, we've actually even reduced the critical current densities required for motion and even increased the mobility of the domain walls with the slope of this curve. And this is really enabled by in situ measurements, interoperando Kerr effect measurements, as seen on the right. And this is not only seen by our group, but it's been seen by many other groups and confirmed a few more times. So this is quite a known phenomenon at this point. So really what's left to engineer are things like the domain wall mobility, or the slope of this curve. And what dictates the slope of this curve, if we go back to the equations of motion, is a few materials parameters. There's the gyromagnetic ratio and the domain wall width, which are actually pretty hard to engineer, or they scale in the wrong direction. So for example, the larger the domain wall width, the larger the mobility, which is not scaling correctly. However, in the denominator of this equation, we have the Gilbert damping, which is actually quite easy to engineer depending on the type of material you have. And in fact, metallic systems, such as all the ones I've shown so far, are actually, the mobility is actually limited by the very large damping because of conduction electrons. However, there's a system that's quite more famous, garnet systems, which have already been introduced in this session, which are famous for not only their low damping, but also their tunable damping. And so what I'll show you is by engineering garnet hybrid metal oxide heterostructures correctly, not only can we drive domain wall dynamics much faster with higher mobilities, but this plateau that you actually see, domain wall velocity, is not the same plateau that you saw for ferromagnets, but in fact, it's a fundamental limit, the relativistic limit of how fast the domain wall can move. And so let me first describe a little bit about these types of garnet materials, more about their structure and their magnetic structure as well. They're very complex oxides. They have very large cells with ions sitting in many different sites. But magnetically speaking, they're actually quite simple. They consist of just 3 magnetic sublattices, an iron tetrahedral sublattice, which is antiferromagnetic coupled to the rare earth dodecahedral site, if you choose to use a rare earth, and of course the other iron sublattice as well. And the interaction between the octahedral site and the dodecahedral site is quite weak, so we typically neglect this. Now, the beauty of these systems is just by choosing this rare earth ion, you can tune a number of different materials parameters, such as the anisotropy. You can even control the dissipation in these materials, and of course, their magnetization and angular momentum as a function of temperature. And here up above, I'm just plotting an example of that, the magnetization as a function of temperature for a variety of different rare earth iron garnets. We can control the compensation, all while retaining very high Curie temperatures in these material systems. So these systems have been around for decades, even in thin film form. They've been around, I think, since at least the 60s, so that's over 50 years. So why is it that we're interested in them now? Well, really, one of the main reasons that we're interested is because we can grow them very high quality with very thin thicknesses. And by thin, I mean just 1 or 2 unit cells while retaining a lot of the bulk properties, like the bulk magnetization. And so this allows us to really use interface effects to drive or dictate magnetic properties. So for example, we can use magnetostriction from lattice mismatch with substrates using epitaxy to induce perpendicular magnetization in these materials. We can also use torques that are driven across these interfaces to induce magnetic switching, which has been shown earlier in this talk, in this session as well, using just currents. And more recently, our group, as well as others, which was described earlier, has discovered things like chiral nail domain walls and chiral exchange interactions across various interfaces in these material systems as well. So this, combined with the damping and the other tunable properties, really give us all the ingredients that we need for ultra-fast dynamics in these material systems. So what actually fundamentally limits the velocity of a domain wall? Well, this is actually a solved problem, solved almost 50 years ago in the 70s by a few different groups. I just named a couple papers here, but it turns out that solitonic quasi-particles, such as domain walls, can really mimic relativistic kinematics. And one way to think about this is a solitary, solitons or solitary wave packets are essentially a superposition of spin waves. So what limits the velocity of domain wall is really what limits the spin wave group velocity. So in other words, maximum velocity of the domain wall is the spin wave group velocity. And this was proven algebraically and analytically by a number of groups in the 70s and 80s. And even more recently, this effect has actually been shown as well using things like computation. So atomistic simulations and other types of simulations have shown that this limit does indeed exist, and they even propose material systems to access this limit, particularly compensated systems. So we chose to investigate this using a specific kind of magnetic insulator, a bismuth-doped YIG sample, bismuth substituted, excuse me. And the advantage of this system is, once again, it's somewhat compensated, so we get fast dynamics. And it has a much lower damping even than other rare earth iron garnets, about a factor of 10 to 100, sometimes even more lower than other rare earth iron garnets. The challenge with this material system is that it's actually pretty difficult to stabilize the DMI in this material. We've had pretty bad luck to stabilize nail-type domain walls. So the domain walls are actually intrinsically immobile. They're the wrong type. They're block and not nail. However, we can get around this kind of cheating in some ways by applying a small in-plane field to the sample to reorient this block domain wall to a nail configuration. This field is larger than the domain wall anisotropy, but much lower than bulk anisotropy of the film, the PMA. And so this is exactly what we did. We can nucleate domain walls and racetracks, apply fields to stabilize nail domain walls, and currents to drive these domain walls into motion. And what you find, again, on the left here is a plot of velocity as a function of current density. And you'll see that these domain walls follow a similar 1D model, where you have a linear regime, saturation regime. Where now the saturation does not depend on the strength of the DMI. It actually depends on the strength of the in-plane field you apply. So the larger the in-plane field, the stiffer this domain wall, more it resists its deformation towards a locked configuration. And this is proven experimentally. So the larger the field that you apply, which is shown here on the legend, the higher this plateau velocity. And what you might notice is the y-axis of this plot is actually quite high right now. So we're in the thousands of meters per second with these domain walls. And in fact, on the right here, I've plotted what the saturation velocity is, or what this plateau is, as a function of the in-plane field. You can see it's indeed quite linear. What's interesting, though, is if we keep increasing this in-plane field, what you'll find is that these curves begin to stack up on one another. And in fact, this saturation or this plateau itself does not get any higher. The plateau itself plateaus, you can see on the right. And so what we find is that this actually can't be explained or couldn't be explained by any existing model of domain dynamics, but could quite easily be explained by the Lorentz contraction of the domain. So this velocity is actually independent of the restoring torque. So no matter how stiff we make the domain wall, no matter how hard we drive the domain wall won't go any faster. And so one can actually calculate the dispersion relationship for this material system. So there's no fitting parameters here. These are all experimentally measured parameters. And what you can find is if you take the derivative of this, you'll get the group spin wave velocity. That's around 5,000 meters per second, which is quite close to what we're seeing. So within 10% of what we see experimentally. Which means that essentially we have to take into account the Lorentz contraction of the domain wall as it's traveling this fast. And so we can analytically and numerically compute what this domain wall Lorentz contraction would be as a function of speed, and even experimentally infer what the Lorentz contraction of the domain wall is from this data, find that these match quite closely. So we've adapted the ferromagnetic domain wall motion equations that I showed you earlier, this 1D model, to account for this Lorentz domain wall contraction. And we can do this analytically with these equations and also using numerical simulations. And what we find is that these models both qualitatively and quantitatively match the experimental data quite well. And so essentially we can access relativistic physics using tabletop experiments. This is all done at room temperature. So this has some practical implications. So it actually tells us what the fundamental limit of how fast these domain wall devices can operate. It also gives us kind of a new playground to study new types of physics as well. I'll just briefly mention before I move on that it's these same compensated magnetic systems that have given us fast domain wall dynamics, but also give us very small spin textures. So we've stabilized some of the world's smallest room temperature skyrmions in these material systems, as small as 10 nanometers in diameter. We can even drive dynamics in these systems, not by using currents or fields, but just by using light. So this work is still ongoing. And we can drive domain walls in skyrmions just by using ultra-fast light pulses. And this is all once again enabled by imaging techniques, either in the lab setting or at a synchrotron, both access this materials physics and apply it in. And so that takes me to the second part of the talk, which I'll go through a little bit quicker because I'm short on time, but it's brand new, hot off the press, where we use perovskites, correlated systems really to control magnon propagation in materials. So one advantage of using spin waves as information carriers is that they can transmit angular momentum over actually a much longer range than spin currents can. So on the order of centimeters rather than just hundreds of nanometers without dissipating. The most touted reason for why people like to use things like spin waves is that magnons don't involve any motion of electrons, and so propagation of magnons involves no Joule heating, which typically means pretty low power dissipations. I think these systems are quite interesting because of the logic and memory operations you can perform. So not only just simple Boolean computing, but also nonlinear computing and even wave-based computing, where you use the functional properties of the wave itself. And in fact, these sorts of technologies are scalable. The smaller you make these devices, the better they perform. I'll just note in particular with antiferromagnetics, we have other additional factors that are advantageous as well, such as higher bandwidths, more robustness against magnetic fields. And from a physics standpoint, you can actually have both left and right-handed polarizations of magnons in antiferromagnets. And so there's been a number of different ways that the community has both created and detected spin waves, both in incoherent and coherent ways, such as using optical techniques or spin pumping and their complementary detection mechanisms, but also incoherent techniques such as using spin Seebeck effect and the inverse spin Hall effect or the spin Hall effect to generate spin waves. So in today's talk, we'll mainly be talking about thermal generation via the spin Seebeck effect and detection, incoherent detection using the spin inverse spin Hall effect. And so a popular way that these are exploited, particularly once again in garnet materials because of their low damping, is by using what's called a non-local spin transport geometry, whereby on the surface of one of these films, you pattern electrodes that are typically metallic, in this case using platinum. It's both a spin source and a spin drain or spin sink. And I mentioned various excitation mechanisms of spin waves. Using this sort of geometry, you can excite spin waves in two different ways. One by using the spin Hall effect, or what they call a spin flip scattering mechanism. It's angular momentum that gets accumulated at the interface, can cause spin wave generation. But you can also just use Joule heating, the spin Seebeck effect, to create a thermal gradient and thus create magnon propagation as well. And inevitably, both of these happen at the same time, but luckily there are ways that we can actually disentangle the effects of both the electronic and the heat-induced mechanisms. So not only has this been seen in ferrimagnets, but also antiferromagnets as well. The common material is hematite, or Fe2O3, and this has been observed both in its easy axis and its plane magnetic configurations. What I'll highlight here is that the main mechanisms of manipulating spin waves from one electrode to the other have mainly been using applied magnetic fields. So all these plots and diagrams use magnetic fields to control how much of the spin wave gets to the detector. There have been a few studies which have used three-terminal type devices, such as this one here. There are a few others as well that use magnonic crystals or magnon scattering to kind of control the propagation of magnons from one terminal to the other, creating some sort of transistor. But in fact, I think there's a lot of opportunities to manipulate spin waves. More importantly, take advantage of the functional properties of spin waves, such as their phase or amplitude. So the question that we've raised is, can we use another stimuli to manipulate magnon propagation, and in particular use electric fields? And the answer is yes, and so the way we're going to do this is by using bismuth ferrite. Bismuth ferrite is a correlated perovskite oxide. It's both an antiferromagnet and a ferroelectric, where both of these order parameters are coupled. So this is the only single phase room temperature magnetoelectric material that we know of. So the ferroelectric polarization actually points along the 111 direction, or the pseudo-cubic diagonal. And it's a G-type antiferromagnet. So in fact, hematite is actually the parent compound of BFO. So they have very similar sort of magnetic structures. So it's G-type antiferromagnet, and it does also have a small Canted moment, which arises from the DMI on the order of 6 EMUs per cc. However, this material is not hexagonal like hematite is. It's actually rhombohedral, which is also a derivative of hexagonal, form of a hexagonal crystal structure. And this mainly comes from the polar displacement that you see from the polarization, as well as very strong oxygen octahedral tilts in these systems as well. But the key thing to keep in mind, the most important thing that you should remember about bismuth ferrite is that the polarization, ferroelectricity, the Néel vector, and the small Canted moment are all orthogonal. So if you get lost, it's just a right-hand rule between all three of them. The other thing to keep in mind is that these three are all coupled. So if I reorient one of them, I also reorient the other two. This has been demonstrated a few times, but if I switch the polarization with an electric field, I also switch the Néel vector and the Canted moment vector as well. So you can get deterministic switching of magnetism in this material. And so can we use bismuth ferrite to manipulate spin transport using electric fields? Well, this is actually a question that's been brought up for over a decade. So Joel Moore and Souza both predicted that this would be the case in bismuth ferrite, and even over a decade ago, there's been some work on manipulating spin wave frequency in bismuth ferrite using electric fields. But here we're more interested in actually using electric fields to control propagation. And so how we do this is we grow this material in thin film form. The challenge with bismuth ferrite is that in its bulk phase, all orientations of the polarization along each cubic diagonal direction are degenerate. So these are all equal likely to form, which means that the magnetic orientation also has 8 degenerate orientations as well. Luckily, we can use epitaxy or atomically precise synthesis and use strain from symmetry breaking substrates like orthorhombic substrates to just isolate 2 of these vectors. So instead of having all 8, we can actually stabilize just 2, which are along kind of across a base diagonal that you can see here. So if you look carefully, the out-of-plane polarization cancels out, but there is a net in-plane polarization. And I'll spare you the details, but we can actually measure this net in-plane polarization using techniques like piezo force response microscopy, which is shown here. And this is actually exactly what the structure looks like that we've designed in between 2 of these non-local electrode devices using platinum as our electrode contact. And so the beauty of this net polarization is that we can actually latch onto this net polarization and use it to control magnetism of bismuth ferrite in the exact same geometry. So by applying electric fields across these platinum electrodes, we can actually oscillate the polarization back and forth in this material with non-volatility, which also means we control the magnetism. So we can do this all while doing this non-local measurement. We create magnons thermally and measure them electrically. And so there's a process that we use to do this. We can essentially polarize the material, measure the non-local voltage, and do some checks to make sure that we haven't switched the polarization state after we've measured the non-local voltage. And what you find is that when we do this, here you're seeing a measurement, an experiment where we measure the non-local voltage as a function of time. We oscillate the electric field every 100 seconds. You can clearly see that we see 2 different distributions depending on the voltage applied that actually change sign. So we can change the sign of the non-local voltage just by applying an electric field. So why is this actually happening? Well, I can explain this very simply by using this right-hand rule that we know about in bismuth ferrite. So it's quite complicated, so I'll walk you through this arrow by arrow. So as you can see in this configuration, polarization, red arrows have a net polarization to the left. And of course, I've explained that if you apply an electric field, you can orient the polarization in the opposite direction. This also comes with reorientation of the male vector and the magnetization as well. And if you look closely, you'll see that, skip a few things here, you'll see that as we switch the polarization, the magnetic orientation or the canted moment goes from right to left to right. So this is more easily seen if I just take a look at the cross section. What you'll find is that the polarization goes from right to left in one case, and the magnetization canted moment follows that. As we switch the polarization, the same thing, what you'll see is the polarization goes now from left to right, and the canted moment also goes from left to right. Thus, because the canted moment is switching, the types of spin waves, the spin polarization of the spin waves that transfer the material are opposite, and thus you get different signals across the platinum electrode. So by controlling the polarization and thus the canted moment, we can control the sign of the non-local. In fact, we can do a hysteresis measurement where we measure the hysteretic response of the non-local voltage with an electric field, and we find that that the coercivity here of this hysteresis closely matches with the polarization hysteresis loop. So indeed, the non-local voltage is switching with the polarization switch. We can do some control measurements, for example, on YIG, which is not a ferroelectric, so we don't expect any sort of ferroelectric hysteresis, and thus we don't see any non-local voltage change. So we know it's not any circuitry of the system that's causing it. We can also do this on a ferroelectric, which is not magnetic, which has, of course, a ferroelectric hysteresis loop, but has no non-local change as well. So this proves that it's not a dielectric effect enhanced from the ferroelectricity that's also causing. So I think I'm over time. So what I'll do is I'll summarize really quickly. I hope I've shown you that by using atomically precise synthesis, combined with some unique ways of image materials, that we can understand some new physics, both in controlling domain wall propagation as well as magnon propagation in oxide material systems, and look at new physics, exploit new functionalities. So with that, I'll end here. I'll thank once again all the collaborators at MIT, Berkeley, and across the world. And I'll finally highlight that I also just started a group at Brown, and we are hiring at all levels. So if you're interested in using atomically precise materials to look at spintronics or other quantum effects, feel free to shoot me an email. So with that, I'll thank you for your attention, and I'm happy to answer any questions.
Thank you very much. So, are there any questions?
Thanks for the very nice talk. I have a question on the relativistic motion of domain walls in bismuth substituted Idrimer and Garnet. So you plot experimental contraction of the domain wall width. So how do you measure this?
Yeah, good question. See if I can find it for you. Back up. Should be. So we don't measure it directly. So we measure it essentially. If you look, you essentially normalize what the maximum velocity that you're currently at is to some control, some velocity at low in field where you see the saturation. So by using that, if you look at the paper, it's more directly in the paper. But if you do this sort of ratio, a lot of things cancel out. Estimate a normalized domain wall width just from this data that you see on the screen. So we're not measuring directly, we're just inferring it from the experiment. And so it's basically a sanity check to make sure that contraction that we're seeing agrees, or that we're inferring agrees with what we're seeing from the model. So this sort of saturation of the saturation isn't in fact coming from some other effect. It's in fact coming from it's more of a sanity check thing.
And in the measurements of the magnon in the bismuth ferrite, so you measure also the first harmonic. So you say that you thermally excite the magnons, but do you see anything in the first harmonic measurements?
Yeah, good question. I don't think I need a slide for this, but so yeah, we measured the second harmonic in the experiments that I showed. If we measure the first harmonic, we don't see anything. And the reason we don't see anything has to do with the domain structure. So if you look at what it looks like between the two electrodes, these domains are actually oriented parallel to the electrodes. And these domains of the different polarization of bismuth ferrite are actually elastic in nature. So there's a structural change across each of these ferroelectric boundaries. And we expect that this is causing a lot of magnon scattering, essentially. And so you don't see any first harmonic. What I will tell you is that there are students working on what's called single phase BFO, single domain BFO, where you don't have any domain walls, and then you do indeed see a first harmonic. So you can get the electronic effect if you're able to engineer kind of these 8 degenerate polarizations of bismuth ferrite correctly.
Okay, thank you.
Yeah.
So if there are no more questions, I think we should really move on because we are quite late. So thanks a lot for this nice talk, and see you next time. So since we are late, we are going to have only a 5 minutes break, and then we come back soon, very soon. So this was
this afternoon. And the next invited talk will be given by Professor Kirill Gadanshevchenko from University of Nebraska-Lincoln. He will talk about spin orbit torque in metallic bilayers and trilayers from first principles. Kirill, please go ahead whenever you're ready.
Thank you very much. Can you hear me and see my presentation?
Yes.
Okay, great. So greetings from Nebraska. I will talk about spin orbit torque in metallic bilayers and trilayers with first principles calculations used as a tool. So here's a brief outline. I'll say a couple of words about the mechanisms of spin orbit torque, then on to the methodology and the results for bilayers and then trilayers. So this is a typical device structure for a spin orbit torque bilayer. We have a layer of heavy metal that has strong spin orbit coupling and a ferromagnet, and thanks to charge to spin conversion, the current that flows in the plane gives rise to a torque acting on the magnetization, which can be used to switch the magnetization or drive high-frequency precession or move skyrmions or other spin textures and do lots of interesting things with magnetic dynamics. There are a couple of simple mechanisms that are well known for the spin orbit torque. So one is the spin hole current, which is generated from the heavy metal and gets absorbed by the ferromagnet, which leads to this kind of angular dependence. This is called a damping-like torque, and its angular dependence looks like this. Another effect is the inverse spin galvanic effect, also called the Edelstein effect, which appears due to the development of a non-equilibrium spin accumulation in the surface bands, which can exert torque on the adjacent magnetization through an exchange field. And this leads to an angular dependence that is called the field-like torque, which acts just like an external magnetic field. But there are other mechanisms that can contribute to the spin torques, which have come to prominence recently. So interfaces can themselves generate spin currents due to the interaction of the electronic spins with the K-dependent effective magnetic fields at the interface. Ferromagnets themselves can generate spin currents of various kinds. There are intrinsic and extrinsic mechanisms that may need to be taken into account. And there may be symmetries beyond damping-like and field-like torque. And we'll see one of them in the following in this talk. In addition, spin torque structures typically are strongly disordered, so there is no clear separation of length scales. The thickness of the layers, the mean free paths, and the spin diffusion lengths can all be of the same order of magnitude. So this makes it more difficult to apply phenomenological models. And on top of this, in tri-layers, as we'll see in the following, there can be crosstalk between different layers due to mean free path effects that can lead to additional types of spin orbit torques. All such mechanisms can be captured by material-specific ab initio simulations in realistic disordered systems, and such calculations can be used as sort of a computational experiment with results suggesting new mechanisms, and they can be compared to simpler models to understand which processes are the most important in a particular system. So a couple of words about the methodology. We use the non-equilibrium Green's function formalism. There's an active region where scattering happens, and this region is attached to the leads that can have different electrochemical potentials. One can calculate the lesser Green's function, which can be used to evaluate the expectation values of observables, such as the torque, which is described by this operator in DFT. And a disorder can be introduced explicitly in the system by taking a sufficiently large supercell for the active region, introducing disorder in the form of either Anderson random potential or substitutional alloying, or whatever you want to include, and then averaging the results over the configurations of that disorder. So here's a benchmark for this calculation. The spin Hall conductivity in platinum. So we will take a non-magnetic system, just a film of platinum. And from this spin continuity equation, one can recover the spin current flowing between any two layers in the film by evaluating the expectation values of the spin orbital torque and summing them up from the vacuum to the given layer. So if one does that calculation for a 100 monolayer platinum film, these are the results that we get. So this is the spin current as a function of the position inside the film for different amplitudes of Anderson disorder. And then the value of the spin current in the middle of the film usually is simply equal to the spin Hall conductivity. If backflow is important from the inhomogeneous profile of the spin accumulation, it can be subtracted, but there is no need to do this in most cases in a film this thick. So this is the result for the resulting spin current flowing in the middle of the film. As we see, there is this characteristic shape with a peak at the Fermi level and the negative conductivity in the regions below the Fermi level. There is very little dependence on disorders. There's a little peak here, but this is actually due to backflow. And we can compare this with the calculation of the intrinsic spin Hall conductivity from the Kubo formula. This is pretty much just the integral of the Berry phase over the integrated part of the, or the filled part of the electronic bands. And we see that the shape is very similar. The amplitude, the magnitude is actually also quite similar. So what this tells us is that the spin transport in platinum is consistent with the intrinsic mechanism. So essentially no disorder dependence, and agrees with the Berry phase calculation. But note that this is a very different kind of calculation. There is no linear response calculation here. It's just a disordered platinum film, and we explicitly calculate the spin current and average it over the disorder configurations. So it's quite reassuring that it reproduces the known result in platinum, where the spin Hall effect is believed to be due to the intrinsic mechanism. So one more tool that we need to analyze the spin orbit torque is how to represent its angular dependence. So it can be quite complicated in general. It can go beyond the damping-like and feel-like terms. So we use the orthonormal basis of real vector spherical harmonics to represent this dependence. This is a set of functions that is known from electrodynamics. Each of these harmonics, those are vector functions. Each of them has a definite parity on the time reversal, either even or odd. And there are two types of these functions. Type 1 is purely damping-like, and it can contribute to magnetization damping and affect the width of the FMR resonance. Type 2 is purely feel-like, which means they are derivable from an energy functional. And notice that the feature of being damping-like and feel-like does not come along with parity on the time reversal. So the leading damping line term is even in magnetization, for example, but as you go to higher values of L, the parity will alternate. So these are the first few harmonics. The 1 - 1 type 1 is the damping-like. And the color here shows the contribution to damping. So it's proportional to my for the damping like this lower harmonic. The feel-like torque is the lowest order allowed harmonic type 2. And then we'll also meet with the planar hole-like harmonic, which is shown here. It's type 2-1. Type 1 indices 2-1. So it's actually odd in M, but it's damping, and it contributes to damping as this MXMZ product. So in practice, we calculate spin orbit torque on multiple points on the sphere for multiple orientations of M, and then the data can be projected onto the set of these harmonics because they're orthonormal. That unambiguously determines each term individually. So now switching to the results for the bilayers. This is a typical setup. So this is a cobalt platinum bilayer. There is vacuum separating this part of the system from its periodic images. And then Anderson disorder is introduced here to tune the resistivity of the system to where it is experimentally. One can also use substitutional disorder, which we used for a different work, which I'm not going to talk about here. This is just for an illustration of band structure of the system. As you can see, very complicated. So one needs to use first principles calculations to get an accurate result. So this is the result for the angular dependence of spin orbit torque in this cobalt platinum bilayer. Each arrow here shows a calculated point. And here the even and odd parts are separated. We can see that the even part looks essentially like the conventional damping like torque. All the arrows point to the towards the y-axis. The odd term is more complicated, and this is the dependence on the disorder strength. Less disorder on the left, more disorder on the right. So the even part looks pretty much the same. The odd part does change a lot. And the reason is that the odd part contains both the feel-like torque and the C2-1 harmonic, which is the one I showed on the previous slide. That's the planar hole-like harmonic. So here are the results of the projection for different disorder strengths, so more disorder to the right. First, we see that the damping-like component is essentially independent of disorder, which is consistent with the expectation based on the intrinsic mechanism. The feel-like torque, which is this line here, it's appreciable at weaker disorder, but gets strongly suppressed as disorder is increased, which is also expected from the Edelstein effect. And finally, we have this planar hole-like harmonic, which is also appreciable. It's considerably smaller than the leading damping-like term, but it is appreciable, and it also, like the damping-like component, essentially independent on disorder. So we'll talk about it a bit later. Let's first look at the thickness dependence of the damping-like torque. So spin diffusion model gives this sort of thickness dependence for the damping-like torque generated by the spin Hall effect. So it starts from 0 in the limit of 0 thickness of the normal metal layer, and then it saturates at the length of the order of the spin diffusion length. And this is the result of the calculation for two systems and two different disorder strengths. So what we see here is that this damping-like torque does not go to 0 as the thickness of platinum is sent to 0. So there appears to be a finite intercept, and we have to interpret this here as an interfacial contribution, as opposed to the bulk contribution that looks like this. So we have to add a constant here to the fit, and this represents this interfacial contribution. And the results of the fit show that the interfacial and the bulk terms are comparable, and in fact, the interface term can even be larger. This means that there are mechanisms that are not reduced to the bulk spin-Hall effect that can generate damping-like spin-orbit torque in a bilayer. The results for the spin-Hall angle and the spin diffusion length are generally in the range seen in experiment. So let's look at the planar Hall-like torque then, which is the non-trivial angular dependence that I mentioned before. So again, as I already explained, both the leading order damping-like and this planar Hall-like torque are essentially independent of disorder. The thickness dependence of the planar Hall-like torque is similar to the damping-like torque. At least we see that it increases with thickness. There is some noise here because it's small. Notice it's scaled up by a factor of 10, but it generally correlates with the leading damping-like torque. And we can also probe the origin of this term by turning off spin-orbit coupling in different parts of the system. And it turns out that if we turn off spin-orbit coupling in cobalt, then essentially nothing happens to these two terms. But if we turn it off in platinum, then both of these terms are strongly suppressed and essentially become zero. So this tells us that the source of both of these is in platinum. We know this for the damping-like torque, but for the planar Hall-like torque, it tells us that this effect in our calculations actually doesn't come from the planar Hall effect in cobalt, which requires spin-orbit coupling in cobalt. There were measurements of this planar Hall-like torque using ST spin torque FMR by Safransky and co-workers in this paper. So they measured the line width, current-induced line width change in two planes. The XY plane here is sensitive to the damping-like torque, and the XZ plane is sensitive to the planar Hall-like torque. So the ratio of the two, if we calculate that from our results, it is in fact quite similar to the results for the platinum ferromagnet system that they used, but they also see this effect of a similar magnitude with gold and palladium. In our calculations, the effect in those systems is much smaller. So this suggests the mechanism could be different. And the two possible mechanisms that have been proposed is the planar Hall effect in ferromagnet that somehow generates spin torque through the longitudinal spin accumulation. It's not quite clear how that happens, but it seems generally consistent with the experimental results. The other possibility is the spin Hall effect in combination with anisotropic interfacial spin relaxation can also lead to this effect, as was shown in this paper, and our results appear to be consistent with this mechanism. So there's only a small amount of data available experimentally and theoretically as well, so more work is needed to understand the mechanisms of this effect. So now I'll turn to tri-layers. So tri-layers can add more complicated symmetries, which is essentially the interest in studying them. For things like field-free switching, it's important to break certain symmetries. So let's consider what kind of torques we can expect in a system where we have two ferromagnets and perhaps the source is in one part of the system that can generate spin currents and whatnot, and then there's a detector that will respond to that. So generically, if we look at the torque on layer 2, we can imagine or expect that it's a combination of a damping-like and field-like torque, but the orientations of the polarizations for those terms can depend on the magnetization of the other layer. So one can write an expansion like that. So for example, S here is the Z cross E, which is the Y direction with the standard choice of axes where the current flows in the X direction. So the terms proportional to S will just give the conventional torques that exist in a, and the only ones allowed in a system where there is no other ferromagnet. But there are additional terms here, and many of them have a known interpretation coming from various effects, coming from the generation of the spin current by the ferromagnet or its interface with the normal metal. But there are also two terms here that are not conventional. Those are non-local M1 dependent field-like torques acting on M2, so they contribute to this F2 here. And these torques are essentially absent in spin diffusion models, or at least they're expected to be very small. Now, as we'll see, these torques are actually possible and can be sizable, and they can result from interlayer crosstalk or mean free path effects. So essentially, electrons sampling both magnetic layers before getting scattered. So this is a similar mechanism that is instrumental in the current in-plane GMR, which is the effect that sort of started the spintronics field. So first, let's look at the torques acting on each layer for parallel and anti-parallel orientations of the magnetizations. So similar to the case of CIP GMR, where the conductance depends on the relative orientation, we see here that the torque acting on each layer depends on the relative orientation of the two layers. So this is not expected in the spin diffusion model, but the effect is very large, especially when disorder is weaker. And the giant magneto-torquens ratio can reach a few 100%. So this is sort of reminiscent of the CIP GMR, and it declines with the thickness of copper. So with this in mind, I want to focus on the torques and the angular dependence of the torques while keeping the two magnetizations orthogonal. So I minimize the input from the CIP GMR into the results. So in this way, all the angular dependence will come from different ways the spin-orbit coupling gets itself into the business, rather than through the dependence of the relaxation times on the relative orientation of the magnetization. So if we pick a certain direction of M1 and we turn off spin-orbit coupling in the second layer, we can calculate the torques acting on M2, and we'll know the source of that torque is somewhere in M1. This helps understand the mechanisms a little better, and one can always add the two kinds of torques coming from spin-orbit coupling in different parts of the system. So we consider the cobalt-copper-cobalt system here. We did this for permalloy as well with similar results for this torque, but I'll focus on this one. And we can calculate the two components of the torque acting on M2 as a function of the angle that M2 makes in the XY plane. And this is what we get here. There are two components. The component proportional to the cross product of the two magnetizations is conventional. One can show that it comes from the spin Hall effect generated either by the interface or by M1 itself. So I'm not going to focus on that because it's conventional, but the other one is unconventional. This is the blue line here. It's a component of the torque that is parallel to M1. And this component is not predicted by the spin diffusion model. At the very least, it's expected to be small because it requires both a precession of the spins at the interface here and an imaginary part of the spin mixing conductance here. So neither of that is expected to be large, but this term is actually very competitive with the leading spin Hall-like torque. So one can do this for different orientations of M1, and overall one can fit this torque to this form. And this form is equivalent to this contribution to the effective field induced by the current in magnetization M2, which is odd in M1 and goes as cross product M1 cross Y. So to understand this, we have done semi-classical simulations using the Boltzmann equation. So this is a collaboration with Vivek Amin, who did these simulations. So in this calculation, all the layers are, for simplicity, assumed to have the same spherical Fermi surface. So the magnetism comes through spin-dependent and spin flip impurity scattering. So the linearized Boltzmann equation looks like this. So it has the electric field part and the spin precession around the exchange field, which controls the absorption of the spin current flowing into the ferromagnets. So this is the impurity part, and then one adds the bonds, which account for all sorts of permutations of the spin current that can happen at the interface. And that is an essential piece of the puzzle. So those come through the boundary conditions, and those are obtained from the simple model for the interfacial potential. So then all of this is solved numerically. And indeed, we can get a angular dependence of the torque that is similar to what we found in first principles calculations. Now, the magnitudes and phases do depend on various parameters, but one can find reasonable parameters where this angular dependence is reproduced. And importantly, the amplitude of this term that is proportional to M1 declines exponentially as the thickness of the normal layer gets larger compared to the mean free path in the normal metal layer. So it comes from crosstalk of the two layers on the scale of the mean free path. How does that happen? So here is the mechanism that we propose to explain this. So here we recall that because there is a spin polarized current flowing in layer 2, and the normal metal layer is not large compared to the mean free path, this current leaks out into the normal metal, and it can reach the interface with the other ferromagnet, and that interface has spin-orbit coupling, and it can transmute spin current into different components. So this current parallel to M2 can get converted through those interfacial processes into the out-of-plane spin current, which is polarized parallel to M1. Then get that current, reaches the interface with M2, and gets absorbed to the spin transfer mechanism. But because it depends on M2 to begin with, there's an extra dependence that turns it into a field-like torque. So this is essentially the mechanism. So to summarize, ab initio calculations present a realistic spin-orbit torque analysis tool, and I showed you some results for both bilayers and trilayers. You can look at these papers for more details, and these are my collaborators and acknowledgements. So thank you for your attention, and I'm happy to answer any questions.
Great, thank you very much, Kyrio, for a beautiful talk. Do we have any questions for Kyrio? Yes, yeah.
Hi, Kirill, this is John Avji. Thanks for this nice talk. I have a question. So when you explained, I think it was in slide 17, that, you know, in the diffusion model, you don't expect, no, maybe earlier. Yeah, here. So the torque tau 2, which is basically parallel with M1, right? Then you said that this is the unexpected torque that you try to explain. But I mean, if you do like a current, I mean, CPP GMR experiment, then you would expect this torque to occur, right? I mean, if you inject a current along the z-axis, and why not?
Yeah, but this is not CPP. This is CIP. The current flows parallel to the interfaces.
But again, I mean,
yeah, so
in that case, you would, I mean, the current that goes through the copper arriving at the cobalt, then I would expect it to be polarized along the M1 such that it can be scattered at M2 to give rise to the GMR. So I don't know if I'm missing something important, that why do we do not expect you know, a spin current with the component parallel to M1?
Well, this component is possible, but you can just write the spin diffusion equations with proper boundary conditions, and you can see what kind of components are expected. So the dominant component that we always expect, that is polarized as in the spin Hall effect. So this would be the spin current flowing perpendicular to the interfaces with the spin polarization along Y. Okay, so if it just gets absorbed, it would give you torque in the Y direction. Or if there is an imaginary part of the spin mixing conductance, it will give you a component rotated about M2. Now, one can also get a rotated component that is a cross product of Y and M1. And that can generate this, torque in the direction of M1, but it's supposed to be small because there are two small parameters. Now, there is no current polarized along M1 in the absence of M2. It's just forbidden. If you remove M2, there is no spin current flowing in the Z direction with the polarization of M1. So it can only appear through the interaction of M2 and M1. It's just the way the CIP current geometry works. So this is the reason.
Okay, maybe a follow-up question then. Well, I mean, yeah, I could not follow 100% your, you know, like the last couple of slides, but you basically explained that the leakage spin current, basically, that goes out of M2, reaches the interface with M1, and then comes back to apply torque. So that's what you are suggesting. Okay.
Yes.
And what about this spin current leakage? So if that happens at M2, it could also happen at M1 with the polarization parallel to M1.
Well, this current flows in the plane. So this arrow, the bigger arrow shows the direction of the current, and the smaller arrow is the spin polarization.
Okay.
So it's not that this current flows in the direction perpendicular to the layers. It's just that because of the finite mean three path, this boundary becomes kind of fuzzy, right? So this current leaks out in the sense that the boundary is smeared out. So this is still a little bit F2. Okay. So this tail then gets converted at this interface, and this requires spin orbit coupling here. Remember, we turned off spin orbit coupling everywhere here. So if there was spin orbit coupling here, then everything could be converted on either interface, right? But here, spin-orbit coupling is only allowed here. Okay, so here, this current here gets converted into the current that flows out of the plane. There's nothing like that here. So this interface cannot convert an in-plane current into an out-of-plane current. Okay? Now, there is a torque acting on M1 as well. I just didn't talk about it, but the same processes would lead to unconventional torques acting on M1. So if spin orbit is allowed everywhere, there will be both kinds of torques. Right? But if we turn off spin orbit coupling here, then leaking of the current from M1 does not get transformed into anything else. It would just be an in-plane current with the spin polarization, and that's it. So if you turn off spin orbit coupling, there is nothing. Right? This requires spin orbit coupling.
Okay, thank you.
Any other question? Curio, I have one quick follow-up question. How does the model depend on the interface details when you have in realistic experimental systems defects and so on?
So in this model here, the boundary conditions come from this model potential. So this is a delta function, and as a function of z, and there's an exchange in spin orbit coupling. So if you tune these parameters, those boundary conditions will change. So this is going to be material specific parameters. But we did calculations in first principles for different systems, and the effect is generically strong. So permalloy, copper, permalloy, cobalt, copper, cobalt. We also tried cobalt, platinum. Cobalt, the effect is much smaller just because of the spin relaxation in platinum. But the things that are going to change are the relative amplitudes and the phases of these curves. So the fact that here it looks like more like a sine is material specific. So the phase can change. But the fact that you will get a torque that is collinear with M1 acting on M2, this is generic. Okay, and this is beyond expectations from the spin diffusion model.
Okay, thank you. If there you have more, okay. If there are no more questions, let's thank Curio again.
Thank you very much.
Okay. Okay, so I'm told that there's a programming change. The last speaker is rescheduled to another session, so this brings this final session to conclusion. So let's thank, I guess, all the speakers this afternoon. Yeah,